Welcome to your first step toward mastering the SK0-005 certification, where we will lay the foundation for your success as a server professional. This course is designed to transition you from basic IT support into a specialized role capable of maintaining complex, server-grade environments. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to CompTIA in any way. All trademarks belong to their respective owners. This content is for informational and educational purposes only and is not a substitute for official study materials or professional training. In this introductory module, we explore the essential framework of the CompTIA Server Plus exam and discuss why this certification is highly valued by employers globally. You will learn to distinguish between standard desktop hardware and enterprise-level server components, which is a critical skill for any technician. We will survey the entire course structure, covering hardware installation, administration, storage, security, and the essential troubleshooting procedures required in the field. This course provides a comprehensive roadmap for those seeking roles as server administrators or data center technicians, regardless of your current experience level. By the end of this journey, you will possess a structured understanding of how to manage, secure, and troubleshoot the core infrastructure that powers modern business. The SK0-005 exam is structured into 4 primary domains, each testing your ability to operate within diverse environments including on-premises, cloud, and hybrid setups. Server hardware installation and management accounts for 18% of your grade, challenging you to understand the physical and logical requirements of rack-mounted or blade servers. The largest portion, server administration, makes up 30%, focusing on operational tasks like identity management and system configuration. Security and disaster recovery follow at 24%, ensuring you can protect data and maintain uptime under adverse conditions. Finally, troubleshooting encompasses 28%, specifically testing your command of the CompTIA 6-step methodology to resolve complex technical failures analytically. Choosing the path of a server technician requires a shift in mindset from simple device repair to ensuring 24-hour service availability and data integrity. Unlike desktop systems, servers utilize redundant components like hot-swappable power supplies, ECC memory, and high-performance RAID storage arrays because unplanned downtime often equates to significant financial loss. You will need to familiarize yourself with the nuances of server form factors, hypervisors for virtualization, and the complexities of managing network services at scale. This curriculum builds upon these foundational facts, ensuring you are not just memorizing answers, but internalizing the logic required for professional-grade server administration. The certification acts as a validation of your readiness to handle the rigorous demands of modern data center environments. As we progress through the course, keep in mind that the strategy for passing the SK0-005 is to prioritize consistent understanding over superficial memorization of terminology. Each subsequent module will build upon the last, guiding you through the deployment lifecycle from initial installation to the implementation of strict security policies and robust disaster recovery plans. Whether you are aiming to transition into a full-time career in data center management or simply seeking a tighter grasp of complex server architectures, these modules provide the necessary technical depth. You will be expected to synthesize information across disparate topics, such as how network configuration directly impacts the performance of virtualized workloads. Focus your effort on grasping the underlying mechanics of these systems, and your path to certification will be far more manageable. I look forward to guiding you through these complex topics in the following sessions. Welcome back. In this chapter, we will explore the physical realities of server hardware and the standards governing their installation and deployment. Server form factors dictate how hardware is physically arranged within a data center to maximize density and thermal efficiency. Tower servers, often resembling large desktop computers, are self-contained units that require no specialized racks, making them suitable for small offices or edge locations where infrastructure is minimal. Rack-mount servers are designed to slide into standard 19-inch cabinets, measuring their height in rack units, or U. A 1U server is 1.75 inches tall, while 2U and 4U variants accommodate more internal storage or auxiliary hardware. Blade systems take modularity a step further by housing multiple compute blades in a single chassis that shares power, cooling, and network fabric. This centralized approach reduces cabling complexity and footprint in high-density environments, though it requires specific infrastructure design. When installing rack-mount units, the use of appropriate rail kits, whether sliding or fixed, is essential for safe maintenance and access. Cable management arms must be configured to permit full extension of the server chassis without placing undue stress on sensitive data or power links. Power distribution units reside within the rack to regulate and distribute electricity to these components, and monitoring their load is a vital administrative task. At the core of these servers, the CPU architecture determines compatibility and performance, with x64 remaining the enterprise standard. Multi-core configurations are now ubiquitous, allowing operating systems to distribute workloads across processing threads to improve throughput and responsiveness. Thermal management represents a significant engineering challenge as these processors generate substantial heat under load. Server chassis incorporate high-velocity fans and air baffles to ensure laminar airflow across the motherboard, which must be unobstructed by cabling or damaged components. Memory selection is equally critical to stability, particularly with the transition from DDR4 to the higher bandwidth DDR5 architecture. Enterprise environments exclusively require error correction code, or ECC, memory to detect and rectify common data corruption incidents. Multi-channel memory configurations further enhance performance by allowing the processor to access multiple memory modules simultaneously, effectively increasing the available bandwidth. Expansion capabilities are facilitated by the PCIe bus, which provides the high-speed interface needed for network adapters, host bus adapters, and hardware RAID controllers. In high-density servers where physical space is at a premium, riser cards are used to orient expansion cards horizontally, allowing for cards to be added without increasing the overall height of the chassis. Beyond the hardware itself, the surrounding environment must be strictly regulated to prevent premature equipment failure. HVAC systems maintain specific temperature and humidity ranges to avoid both electrostatic discharge caused by low humidity and potential oxidation or cooling inefficiency in overly humid conditions. Hot and cold aisle containment strategies prevent the mixing of air, ensuring that cool air is directed solely through the front of the intake side equipment. For critical infrastructure, fire suppression systems such as FM200 or Novec 1230 are preferred over water-based systems because they extinguish fires by disrupting the chemical reaction without damaging electrical components. To facilitate administration, out-of-band management solutions are mandatory in professional data center operations. KVM switches allow a single console, comprised of a keyboard, video monitor, and mouse, to oversee multiple servers, regardless of their operational power state or operating system status. Modern servers often implement these functions via a baseboard management controller, which enables serial console access over a network. This out-of-band visibility ensures that administrators can troubleshoot boot issues or configuration errors even when the primary network interface or operating system is unresponsive. Physical security must not be treated as an afterthought in this context. Biometric locks provide a reliable audit trail for who accessed the server room, while environmental sensors constantly monitor for leaks, unauthorized door openings, or temperature spikes. These combined hardware and environmental strategies ensure that the server infrastructure remains available, performant, and secure against both internal and external threats. See you in the next lecture. Welcome back to our journey through the server environment, where today we focus on the foundational layer of any server infrastructure, the operating system. In this chapter, we will master the intricacies of selecting, deploying, and managing server operating systems to ensure stability and efficiency. Choosing the right operating system involves a calculated assessment of your specific business requirements and the existing ecosystem of applications. Windows Server remains the industry standard for environments heavily reliant on Active Directory, group policy, and proprietary Microsoft software, offering a coherent management interface that many enterprises find indispensable for their administrative workflows. Conversely, Linux distributions such as RHEL, Ubuntu, and Rocky Linux provide a modular and often more performant foundation for web services, containerization, and back-end infrastructure. While RHEL offers enterprise-grade support and stability, Ubuntu is frequently favored for its vast package repositories and developer-centric availability. Understanding the differences between these systems is not about picking a favorite, but rather about matching the kernel architecture and support lifecycle to the specific service you plan to host. Deployment strategies have evolved from manual installations to highly automated provisioning pipelines that minimize human error and ensure configuration drift is kept to a minimum. For small deployments, booting from a local USB drive is a functional starting point, but in data center environments, PXE boot services are the preferred method for diskless or remote imaging workflows. By utilizing pre-boot execution environment, an administrator can trigger an OS installation over the network, connecting to a distribution server that pushes the image directly to the hardware. Following the base OS installation, essential post-deployment tasks such as driver validation, unique system naming conventions, and static IP configuration are mandatory to prepare the server for production. These foundational steps ensure that the server is reachable and performant from the very first moment it joins the network. Once the operating system is online, effective management depends on your ability to leverage the right tools for the right tasks. Microsoft Management Console, MMC, serves as the traditional hub for task-oriented administrative duties, while PowerShell has become the indispensable standard for automating repetitive, complex operations across multiple Windows nodes. In the Linux world, Bash remains the primary shell for administrative tasks, but the integration of Python has drastically improved the ability to create robust automation scripts for configuration management. Effective monitoring is equally critical. SNMP provides a standard protocol for collecting performance data from devices across the network, while syslog serves as the backbone for centralized logging. When we need to visualize the current load or resource consumption of a Windows server, we rely on Performance Monitor to track metrics such as CPU saturation or memory utilization over time. The life cycle of server hardware extends far beyond the initial purchase order and operating system deployment. Asset management is a disciplined practice that begins at procurement and ends only after the equipment has been properly retired and decommissioned. This process demands that we maintain accurate records of every server, including its serial number, location, and the software licenses it consumes, allowing us to accurately forecast needs for expansion or replacement. When a server reaches the end of its useful life, we cannot simply discard the hardware without ensuring the absolute destruction of the sensitive data residing on the storage media. Data sanitization compliance requires rigorous adherence to standards that mandate either physical destruction of the drive or advanced cryptographic erasure techniques. By following these structured life cycles, we ensure that both our investments and our data remain secure from procurement through final disposal. See you in the next installment of our series. Welcome to our deep dive into identity and access management, where we will translate abstract security concepts into robust, actionable server administration practices. This chapter provides the essential architecture you need to secure any enterprise environment against unauthorized access. Identity and access management is the cornerstone of server security, focusing on who can do what within your infrastructure. Role-based access control, or RBAC, is our primary tool here, allowing us to assign permissions based on job functions rather than individual user accounts. By implementing the principle of least privilege, we ensure that every user and service account possesses only the minimum set of permissions necessary to perform their required tasks. This minimizes the attack surface, so that if a credential is compromised, the potential lateral movement by an attacker remains limited. We achieve this hierarchy through Active Directory, where forests and trees define our trust relationships and organizational boundaries. Managing organizational units allows us to categorize objects logically, simplifying the application of security policies across departments. Security groups then bundle permissions, making it far easier to manage access for 50 users than auditing individual permissions manually. Centralizing this management relies heavily on group policy objects, which form the bedrock of environment standardization. Through GPOs, we can enforce configuration settings, such as password complexity requirements or local access rights, across every machine in our domain simultaneously. This centralized hardening is far more reliable than manual configuration, as it eliminates human error and ensures uniform security posture across the server fleet. When users attempt to interact with these resources, they engage with authentication protocols like Kerberos, which provides secure ticket-based authentication, or the lightweight directory access protocol for querying user attributes. Radius serves a distinct purpose, acting as a standard for authentication, authorization, and accounting in remote access scenarios. We must also distinguish clearly between local accounts, which exist only on a single host, and domain accounts, which leverage the centralized directory service for enterprise-wide access. Relying on local accounts for core administrative tasks usually indicates a failure in proper domain management strategy. Security is no longer a static perimeter, so we must adopt modern practices like multi-factor authentication and just-in-time elevation. Implementing MFA for server access remains one of the most effective deterrents against credential theft, as it requires a secondary form of verification. For administrators working in high-security environments, we utilize privileged access workstations to ensure that administrative actions occur from a cleanly hardened, dedicated device. This prevents compromise via malware residing on a jump host or a standard user's laptop. When we need to perform elevated tasks, we shift away from standing privileges in favor of just-in-time access. This methodology elevates a user's permissions only for the duration required for a specific task, effectively killing the persistent threat of always-on administrative rights. Remote management remains constant, with SSH and RDP as our primary protocols, provided they are restricted behind these layers of authentication and access control. Finally, we must reconcile our policies with reality through auditing and logging. Security is not a set-it-and-forget-it task. We need to actively monitor our environment to detect anomalies. By configuring robust access logs, we can reconstruct the history of an account interaction or identify attempts at privilege escalation in real time. We look for patterns where a standard user account suddenly attempts to access sensitive files or modify system settings that fall outside their assigned scope. This requires a proactive approach to centralization, feeding logs into a SIEM or a similar analysis engine that alerts us when threshold boundaries are crossed. Through careful administration of organizational units, rigorous application of group policies, and disciplined use of JIT elevation, we establish a robust environment. This framework protects data integrity and ensures that accountability remains high even as our configurations grow in complexity throughout the enterprise lifecycle. I will see you in the next lecture. Welcome back. Today we are diving into advanced storage and RAID technologies to better understand how we manage data integrity and performance at the server level. This chapter provides the foundation for building resilient storage architectures that form the backbone of any enterprise environment. Redundant array of independent disks, or RAID, is a method of aggregating multiple physical disks into logical units to improve performance or provide fault tolerance. RAID 0, or striping, distributes data across multiple disks, which offers high speed but zero redundancy, meaning the failure of one drive results in total data loss. RAID 1 uses mirroring to duplicate data across two drives, ensuring that if one drive fails, the other maintains a perfect copy, though it effectively cuts your usable storage capacity in half. RAID 5 requires at least 3 drives and uses parity information spread across all disks, allowing the array to recover from a single drive failure while balancing storage efficiency. RAID 6 takes this further by utilizing dual parity, which allows the system to survive the simultaneous failure of 2 drives, although it carries a write performance penalty due to the complexity of dual parity calculations. Nested RAID 10 combines mirroring and striping to provide the high speed of RAID 0 with the redundancy of RAID 1, making it a preferred choice for performance-demanding databases despite the higher cost per gigabyte. When implementing these arrays, you must distinguish between hardware and software RAID, as each impacts system performance differently. A hardware RAID controller is a dedicated physical card with its own processor and cache memory, offloading the heavy computational work from the main server CPU and typically providing better stability. Software RAID, conversely, is managed directly by the operating system kernel, which is cheaper to implement but consumes host resources and lacks the dedicated cache features of a high-end dedicated controller. In terms of physical media, we see a transition from traditional hard disk drives like SATA and SAS toward high-performance solid-state drives, with NVMe protocols significantly reducing latency by communicating directly over the PCIe bus. Choosing between these technologies involves balancing cost, throughput, and the specific input-output operations per second required by your applications. Storage connectivity and architecture dictate how your servers interact with their data silos, moving from simple direct attached storage to more complex networked environments. Direct attached storage is physically connected directly to the server, which is simple to configure but limits scalability and sharing capabilities between different server nodes. Network attached storage operates at the file level over standard Ethernet, allowing multiple clients to access shared files using protocols like NFS or SMB, while storage area networks function at the block level, appearing as local drives to the connected servers. Within the SAN ecosystem, we rely on specific protocols such as Fibre Channel for dedicated high-speed connectivity, iSCSI for carrying SCSI commands over existing IP networks, and Fibre Channel over Ethernet for unified fabric architectures. Managing security in these SAN environments requires LUN masking, which limits specific server access to designated storage volumes, and zoning to isolate traffic on the storage fabric itself. Efficiency and availability within these systems are bolstered by techniques such as thin provisioning and multipathing. Thin provisioning allows you to allocate more storage than is physically available, letting you grow capacity on demand rather than reserving massive blocks of unused storage from day one. Multipathing provides redundant physical paths between the server and the storage system, ensuring that if one controller or cable fails, the I/O request is rerouted automatically, preventing system outages. Furthermore, disk redundancy is enhanced through hot spares, which can be dedicated to a specific array or assigned globally to handle any drive failure across multiple RAID sets. Hot swapping allows you to replace a failed drive in a running system without shutting down, maintaining uptime while the controller rebuilds the data onto the replacement disk in the background. Managing space effectively requires a solid grasp of underlying file systems and volume management tools. NTFS remains the standard for Windows environments due to its robust journaling and permissions handling, whereas refs is optimized for resiliency and large-scale data sets with built-in checksums. On the Linux side, Extension 4 is a reliable, widely supported file system, while XFS is often preferred for high-performance enterprise workloads because of its parallel I/O capabilities. To manage our disks effectively within Linux, we often use the Logical Volume Manager, which provides a layer of abstraction that allows us to resize partitions, span volumes across multiple physical drives, and take snapshots of live systems for backup purposes without unmounting the storage. Mastering these software abstraction layers is just as critical as choosing the right physical drive or RAID configuration because it dictates how data is organized, protected, and retrieved on a daily basis. I will see you in the next lecture. Welcome back. In this chapter, we will master the essential networking configurations and infrastructure services required to maintain robust server environments. Building a reliable server network is not merely about plugging in cables. It is about understanding how traffic flows and how services facilitate communication. We will start with the fundamentals of IPv4 and IPv6 addressing, moving into subnetting, which is vital for segmenting traffic and improving security. Beyond basic connectivity, we will examine 802.1q VLAN tagging and the implementation of virtual switches, or vSwitches, which allow us to logically isolate traffic within virtualized environments. You will learn to differentiate between static routing, where paths are manually defined, and dynamic routing, where protocols negotiate paths automatically. By the end of this module, you will possess the specialized knowledge required to architect, manage, and defend a complex server network infrastructure. Effective network management relies heavily on core infrastructure services that automate the behavior of connected devices. Domain Name System, or DNS, maps human-readable host names to IP addresses, utilizing various record types such as records for IPv4, Quad A for IPv6, MX for mail routing, and name for aliasing. Similarly, HCP streamlines network administration by dynamically distributing IP addresses, gateways, and DNS settings via scopes, while allowing for reservations to ensure critical servers always maintain the same address. Time synchronization via the network time protocol is equally critical, as logs and security certificates depend on precise timestamps across all distributed nodes. These services represent the backbone of server communication, and mastery of their configuration is non-negotiable for a professional administrator. Securing server communication requires a granular understanding of TCP and UDP port usage and the application of firewall rules. You must be comfortable with the specific roles of well-known ports, including FTP on 20 and 21st, SSH on 22 for secure management, and persistent HTTP or HTTPS traffic on 80 and 443. Telnet, while largely deprecated due to its lack of encryption, remains a protocol we identify for historical compatibility, whereas RDP on 3389 is the industry standard for graphical remote administration. Configuring local software firewalls is your primary defense against unauthorized access, while understanding port security on physical switches prevents MAC-based exploits. Consistently applying these controls ensures that only authorized traffic traverses your infrastructure, effectively minimizing the scope of potential attacks. High availability and throughput are non-functional requirements that often dictate our approach to network interface design. Interface teaming and the Link Aggregation Control Protocol, generally known as LACP, allow us to bundle physical network adapters into logical units to increase bandwidth and provide redundancy. If a single physical link fails, the team remains active, ensuring the server stays reachable, which is crucial for modern enterprise SLAs. When connectivity issues inevitably arise, a systematic approach is necessary, employing tools like ping to verify basic reachability and tracert to map the hop-by-hop path to the destination. Netstat serves as your primary diagnostic tool for inspecting active connections and listening ports, while NSLookup allows for rapid verification of DNS resolution integrity. See you in our next session. Welcome to the chapter on virtualization and cloud computing, where we will demystify the architectures that drive modern data centers. You will master the distinctions between hypervisors, cloud deployment models, and containerization to become an indispensable infrastructure architect. Virtualization is essentially the abstraction of physical hardware into logical resources that can be managed independently. At the core of this abstraction lies the hypervisor, which acts as the intermediary between the guest operating systems and the underlying physical server components. We categorize these hypervisors into two primary types based on their execution environment. A Type 1 hypervisor, often referred to as bare metal, sits directly on the physical hardware, which allows it to provide superior performance and efficiency because it does not rely on a host operating system. Examples here include VMware iSCSI, Microsoft Hyper-V, and the open-source KVM. Conversely, a Type 2 hypervisor runs as an application on top of an existing host operating system, which adds a layer of overhead but offers greater compatibility with diverse hardware configurations. Understanding when to deploy a Type 1 versus a Type 2 hypervisor is critical for capacity planning, as the performance requirements of your production workloads should almost exclusively dictate the use of bare metal solutions to ensure consistent resource availability and reliability. Resource management in a virtualized environment requires a nuanced understanding of how hypervisors juggle the demands of various virtual machines. When we allocate virtual CPUs, we are essentially mapping virtual cores to physical threads, and over-provisioning these resources can lead to contention and performance degradation if one virtual machine starves others of processing power. RAM ballooning is another ingenious strategy where the hypervisor reclaims unused memory from guest machines that are not actively utilizing their full allocation, effectively redistributing that memory to VMs under higher pressure. Similar logic applies to storage, where virtual hard disks like HDX or VMDK files are often thin-provisioned to save space while dynamically growing as data is written. However, this flexibility can be a double-edged sword. You must implement rigorous snapshot management because every snapshot taken creates a delta disk file that grows over time. If left unchecked, these snapshots can cripple performance or fill up the underlying storage array, necessitating a proactive approach to disk consolidation and cleanup. When looking at moving workloads between physical hosts, vMotion and similar migration techniques allow for seamless operations without downtime by copying the memory state and CPU context between hypervisors. This capability is fundamental to building a high-availability environment, as it enables the implementation of clustering and distributed resource scheduling. Through clustering, we ensure that if a physical node fails, the virtual machines can be automatically restarted on a remaining healthy host. Distributed Resource Scheduler, or DRS, goes further by monitoring the utilization of clusters in real time and automatically migrating workloads to balance the load across the hardware. This dynamic orchestration is what enables the level of reliability expected in today's enterprise environments. Without these mechanisms, administrators would be forced to perform time-consuming manual migrations during peak hours, which is rarely a viable strategy in production. While virtual machines were the gold standard for years, containerization has introduced a more lightweight alternative by sharing the host machine's kernel instead of virtualizing the entire hardware stack. Tools like Docker provide a streamlined way to package applications and their dependencies into a standardized unit, which eliminates the common issue where a piece of software works on a developer's machine but fails in production. Kubernetes manages these containers at scale, automating deployment, scaling, and the operational management of containerized applications across several nodes. This shift from VMs to containers represents a significant evolution in efficiency, as it drastically reduces the cold start time and memory footprint of services. While VMs remain the better choice for isolating complete operating systems, containers are the clear winner for microservices and cloud-native application development where agility and rapid deployment are the highest priorities. Moving into the cloud, we distinguish between deployment models based on how the infrastructure is shared and maintained, starting with public, private, hybrid, and community clouds. A public cloud offers resources over the internet, while a private cloud is dedicated exclusively to a single organization, often behind an internal firewall for strict control. Many organizations adopt a hybrid approach, keeping sensitive data on premises while offloading transient or less critical workloads to the public cloud to take advantage of elasticity. Service models further refine this landscape into infrastructure as a service, platform as a service, and software as a service. IaaS provides the raw building blocks like virtual servers and storage. PaaS offers a framework for developers to code and deploy software, and SaaS delivers full applications over the network. In all these arrangements, The shared responsibility model is the most important concept to grasp, as it clearly defines which security and maintenance tasks belong to the provider and which remain the customer's burden. The provider typically manages the security of the underlying cloud infrastructure, including the physical data center, server hardware, and the hypervisor layer in the case of IaaS. However, the customer almost always retains responsibility for the security of data, identity management, and configuration of the operating systems or applications running within those services. Misunderstanding this division of labor frequently leads to significant security gaps, as administrators might mistakenly assume that a cloud provider is backing up their files or managing their patch levels just because they are hosting the data. Always verify your role in the provider's agreement to avoid leaving your virtual assets unprotected. Security is not an inherited attribute of cloud computing. It is a shared effort that requires active attention from both the vendor's engineers and your own internal IT team. Integrating this mindset into your operational workflow ensures that your leap into cloud computing remains a secured and standardized transition rather than an unmanaged risk. See you in the next lecture. Welcome back. In this session, we will explore the critical domain of server security and hardening to ensure your infrastructure remains resilient against evolving threats. This chapter is designed to provide you with a comprehensive, professional-grade understanding of how to protect server environments from both physical and digital exploitation, which is a mandatory skill for any certified infrastructure administrator. Securing a server begins with the realization that the hardware itself is the foundation of your trust chain, necessitating a multi-layered security approach. We start with physical security, as no amount of software configuration can mitigate a compromise if an adversary has direct access to the chassis. Implementing robust measures like physical server locks and chassis intrusion detection switches ensures that any unauthorized opening of the server housing is logged and alerted upon. Beyond the rack, high-definition camera surveillance provides an audit trail for the facility, while badge access systems restrict entry to authorized personnel only. You must treat the physical environment as an extension of the logical security boundary, ensuring that peripheral ports are physically blocked or disabled when not in constant use. This holistic perimeter control helps prevent the insertion of malicious USB drives or unauthorized hardware bridge devices. When you design your security posture, assume that any physical access is equivalent to total system compromise, and prioritize your facility controls accordingly. Once the physical perimeter is established, our focus shifts to data protection, specifically addressing data at rest through robust encryption standards. Encryption is not merely a checkbox, it is a fundamental control ensuring that if drives are stolen or misplaced, the data remains unreadable. Technologies such as BitLocker for Windows environments or LUKS for Linux provide full disk encryption that transparently secures data at the sector level. Alternatively, self-encrypting drives, or SEDs, offload the cryptographic operations from the server processor directly to the drive controller, ensuring performance remains stable even under heavy I/O loads. For data in transit, we rely exclusively on SSL and TLS protocols to establish encrypted tunnels that prevent eavesdropping during network communication. Managing these identities requires a public key infrastructure, which provides a structured way to issue, renew, and revoke certificates. Without a disciplined approach to certificate lifecycle management, you risk expiration-related downtime or, worse, man-in-the-middle attacks resulting from untrusted or misconfigured root authorities. Hardening the system begins at the lowest level of software, specifically within the BIOS or EFI environment, where we systematically reduce the attack surface. You should start by disabling all unused interfaces, such as serial ports, integrated audio, or secondary network controllers, as these are often overlooked vectors for initial access. Implementing a strong administrator password at the firmware level prevents unauthorized changes to boot priorities, which is critical for maintaining the integrity of the operating system boot process. By enabling secure boot, you leverage cryptographic signatures to ensure that only trusted, validated code is executed during the startup sequence, effectively neutralizing rootkits that target the bootloader. Furthermore, disabling legacy features like PXE booting on segments where it is not required prevents adversaries from attempting network-based OS injections. Taking the time to curate these firmware settings creates a stable, predictable, and defensible platform before the operating system even initiates its first loading routine. At the operating system level, maintaining a secure posture requires a combination of endpoint protection and proactive vulnerability management. Host-based intrusion detection and prevention systems provide visibility into anomalous system behavior, acting as a sentry that monitors for unauthorized changes to critical system files or privilege escalation attempts. Antivirus solutions remain relevant, but they must be managed as part of a broader strategy that includes disabling unnecessary services and protocols that aren't strictly required for the server's role. Patch management is equally vital, and you should implement standardized workflows using tools like WSUS for Windows-centric environments or repository managers like Yum and APT for Linux distributions. Regular vulnerability scanning allows you to identify missing patches or misconfigurations before attackers can exploit them, turning a manual, reactive process into a disciplined, automated cycle. Complementing this with file integrity monitoring allows you to track modifications to configuration files in real time, which is essential for both security auditing and maintaining operational baselines. Finally, we consider data loss prevention as a final line of defense against the exfiltration of sensitive information, whether accidental or malicious. Data loss prevention solutions can inspect outbound traffic and file operations to identify patterns indicative of sensitive data movement, such as credit card numbers or proprietary intellectual property. These tools act as a policy enforcement point that restricts unauthorized users from moving data to removable media or cloud storage services effectively. While security is often viewed as a restrictive burden, when implemented correctly through these layered methodologies, it actually increases the reliability and predictability of your infrastructure. By minimizing the attack surface and maintaining consistent, patched states across all server assets, you reduce the likelihood of incident response scenarios and ensure that your uptime goals are met with integrity. Always view security as a continuous life cycle of hardening, monitoring, and remediation rather than a static goal. I will see you in the next lecture. Welcome back. In this session, we will examine the principles of disaster recovery and high availability to ensure your infrastructure remains resilient. Business continuity planning is the cornerstone of any robust server environment, as it defines how an organization continues to function during and after a disaster. When we talk about recovery metrics, we focus on Recovery Time Objective, or RTO, and Recovery Point Objective, or RPO. RTO represents the maximum tolerable duration of downtime before an organization suffers significant harm, while RPO defines the acceptable amount of data loss measured in time from the moment of failure. Setting these requirements accurately is a business decision rather than a purely technical one, because lower RPO and RTO values require significantly more expensive infrastructure. You must understand these concepts deeply because they dictate the architectural choices you make regarding storage and site replication. If the business requires an RTO of 0, you are no longer looking at simple backups but at active high availability systems. Data protection relies fundamentally on your backup strategy, which involves different types of backups to balance storage space against restoration time. A full backup captures every piece of selected data, which is simple but time-consuming and storage-heavy. Incremental backups capture only the data that has changed since the last backup of any type, which makes them very fast and efficient in terms of space. Differential backups, conversely, capture everything that has changed since the last full backup, meaning each differential set grows larger over time until the next full backup occurs. Synthetic backups are an optimization where the system takes a full backup combined with subsequent incremental backups and collapses them into a new full backup on the storage media. Choosing between these depends on your backup window and the available bandwidth for moving data. Data rotation and off-site storage strategies like the 3-2-1 rule ensure that your data survives even catastrophic facility failures. The 3-2-1 rule suggests keeping at least 3 copies of your data on 2 different storage media, with 1 copy stored off-site. Grandfather-father-son rotation is a common scheme that uses daily, weekly, and monthly backup cycles to manage these media efficiently. This systematic approach ensures that if a tape or drive is corrupted, you have historical points of recovery available. Remember that backups are entirely useless if they are not verified. You must test restoration procedures periodically to ensure you can actually recover data. An untested backup is merely an optimistic assumption that you have data safety. When considering physical site recovery, we categorize options into hot, warm, and cold sites based on their readiness. A hot site is an identical, fully operational environment ready to take over traffic immediately with minimal RTO. A warm site provides the necessary hardware and network connectivity but might require you to restore data from backups and configure services before it is functional. A cold site simply provides the floor space, power, and environmental cooling, requiring you to ship and install hardware before any recovery can begin. Choosing the right site depends entirely on the critical nature of the workload and the organization's budget for downtime. High availability is achieved through clustering and load balancing, which allows services to remain accessible even when one component fails. Failover clustering allows multiple nodes to share resources, so if one server loses power or crashes, the others take over. Network load balancing, or NLB, distributes incoming traffic across a cluster of servers to ensure no single unit becomes a bottleneck. To support these systems, you need reliable power infrastructure such as uninterruptible power supplies for short-term protection against spikes and brownouts. Long-term power redundancy requires standby generators that can kick in if the primary utility source remains down for an extended period. Capacity planning must be integrated into your disaster recovery design, especially when failing over to a secondary site. If your production environment uses a specific amount of compute and storage, your failover site must be prepared to handle that actual load, not just an idle state. Documentation is the glue that holds these strategies together. Without a formal disaster recovery plan, contact lists, and step-by-step procedures, the best hardware in the world will fail when human panic intersects with technical failure. You should maintain clear records of who needs to be called and which systems must be brought up first in a specific sequence. Geographic redundancy is the final layer, ensuring that even if a natural disaster wipes out your entire region, your data remains accessible in a separate, unaffected location. See you in the next lesson. Welcome back. In this session, we will examine the CompTIA 6-step troubleshooting process, an essential framework for resolving server issues in production environments. Troubleshooting in a professional data center or enterprise environment is rarely about lucky guesses or frantic configuration changes. Instead, it is an exercise in disciplined investigation, where the primary goal is to minimize downtime through a repeatable, logical structure. The CompTIA troubleshooting methodology provides exactly this, forcing you to step back from the immediate frustration of a failing service and engage with the environment systematically. We start by identifying the problem, which is often the most neglected step. You must gather as much data as possible, verify that the issue can be reproduced, and crucially, talk to the users who are experiencing the symptoms. By listening carefully, you can distinguish between a hardware fault, a misconfiguration, or a simple user error, saving yourself hours of unnecessary labor on the wrong component. Once you have a clear grasp of the symptoms, you move to the second step, establishing a theory of probable cause. Here, it is vital to keep your mind open but grounded in technical reality, often starting by questioning the obvious. Before tearing apart a server chassis, check if the power cable is seated or if a simple virtual machine service has stopped. If the obvious is ruled out, Proceed by escalating your theory from the most likely to the least likely scenarios. The third step requires you to test that theory, which is where you must be exceptionally careful. Never implement a fix during this phase. Your goal is only to confirm or refute your hypothesis. If your test fails to identify the cause, discard that theory and move to the next one on your list, maintaining a clean state in the environment whenever possible. After identifying the root cause, the fourth step involves creating a plan of action to resolve the issue while simultaneously addressing the impact on your users. Communication is just as critical as technical skill here, as stakeholders need to know what you are doing and how long the service might be unavailable. Once your plan is prepared, you move to the fifth step, implementation. You apply the fix, and if the complexity or specific nature of the problem exceeds your authorization or capability, you escalate the issue to the appropriate level of support. Always remember that escalation is a tool, not a sign of failure, as it ensures that the business remains the priority over any individual pride. You must document every action you take, as this audit trail is vital for both future troubleshooting and compliance reviews. The final step is verifying that the system is fully functional and, if the situation warrants it, implementing a preventive measure to stop the issue from recurring. This is not simply a matter of checking that the service is up. You should confirm that all related subsystems are performing within expected parameters. Preventive maintenance is the hallmark of a senior administrator, so look for ways to adjust your monitoring, refine your configuration, or update your documentation to harden the system. Documentation must continue from the identification phase all the way through to the final sign-off, as this information populates your knowledge base for future incidents. By relying on this six-step model, you transform troubleshooting from a chaotic, reactive process into a structured, proactive engineering discipline that builds stable, resilient infrastructure. I will see you in the next lecture. Welcome back. Let us explore the intricacies of physical server stability. This module focuses on diagnosing hardware and environmental variables to ensure your infrastructure remains resilient under load. Troubleshooting physical hardware often starts before the operating system even loads. A reliable way to diagnose boot time failures is the power-on self-test process, which provides immediate feedback via beep codes or postcards displayed on the motherboard. When a server fails to initialize, these codes act as the first line of diagnostic intelligence, indicating whether the issue resides in the CPU, memory, or the system board itself. It is essential to understand that these codes are vendor-specific, so you must always keep the technical manual accessible to translate these signals into actionable information. If you encounter a system that halts abruptly during high-intensity tasks, you should first investigate CPU thermal management. Thermal throttling occurs when the processor reaches a critical temperature threshold, resulting in a forced reduction of clock frequency to prevent permanent silicon damage. This behavior usually suggests inadequate airflow, failing heat sink fans, or dried thermal interface material that requires immediate replacement to restore nominal performance. Memory issues are notoriously difficult because they often manifest as intermittent application crashes or spontaneous reboots rather than hard failures. You can identify faulty RAM by observing parity errors or using diagnostic tools like MMTest86, which exerts stress on memory cells to reveal latent defects. When a single module shows signs of degradation, it is best practice to replace the entire set to ensure parity across the memory channels. Storage components, such as mechanical hard drives or solid-state devices, exhibit distinct failure symptoms that demand your immediate attention. A clicking noise from a spinning drive is a classic indicator of a failed actuator arm or read-write head assembly, signaling an imminent total data loss. Modern drives utilize self-monitoring, analysis, and reporting technology to provide preemptive warnings of hardware failure, allowing administrators to migrate data before a critical outage occurs. RAID rebuild failures often occur when an aging drive finally succumbs to the stress of parity reconstruction, underscoring the necessity of maintaining robust, off-site backups regardless of the redundancy level configured in your environment. power delivery infrastructure constitutes a frequent, silent point of failure for high-density server deployments. A digital multimeter is an indispensable instrument for verifying that power supply units are delivering clean, stable voltage to the backplane. When analyzing power fluctuations, you must evaluate the entire path from the uninterruptible power supply down to the individual motherboard rails. If you observe random system resets, it may be that the UPS battery has exhausted its capacity and can no longer bridge the gap during minor input disturbances, or perhaps a circuit breaker is being tripped by an oversized load. In blade server chassis, you should verify the health of the interconnect modules and power distribution units, as these components act as the central nervous system for all blades within the cage. Always ensure that you practice strict electrostatic discharge precautions, such as using grounded wrist straps and conductive mats, to prevent damaging sensitive CMOS components during these invasive physical interventions. Connectivity issues, particularly concerning cabling and backplane integrity, often mimic more complex software configuration errors. If a storage controller reports a link failure, inspect the physical cable for kinks, improper seating, or oxidation on the contacts before escalating to more expensive hardware replacements. Expansion cards must be verified for both physical compatibility with the PCIe bus and logical compatibility with the system's current driver ecosystem. A driver conflict can manifest as a resource contention, locking the system and forcing a recovery process that might involve rolling back to a known stable configuration. Environmental factors, such as ambient temperature or poor site humidity, play a significant role in long-term hardware reliability. By systematically ruling out physical dependencies within the server, cabling, and cabinet environment, you can accurately isolate the root cause and maintain the high availability required in modern enterprise data centers. I look forward to our next session. Welcome back. In this chapter, we will address the complexities of managing and troubleshooting server operating systems, a domain where precision and methodical analysis are mandatory. When an operating system fails to boot, one must distinguish between the bootloader and the kernel configuration. In Windows environments, the boot configuration data, BCD, store is often the culprit when the system fails to transition control to the OS loader. If you encounter errors related to boot devices or missing files, using the command line interface from a recovery environment to rebuild the BCD is a standard remediation step. Conversely, Linux systems typically utilize grub, where misconfigured partitions or missing modules in the /boot/grub/ directory prevent the system from loading the kernel. Repairing these instances usually involves crooting into the system from a live environment to reinstall the bootloader or modify the configuration file manually. Understanding these boot processes is essential because these systems serve as the foundation for every service running on the server. Even when a server boots successfully, it may suffer from runtime instability, often manifested as the blue screen of death in Windows or a kernel panic in Linux. These stop errors occur when the OS encounters an issue from which it cannot safely recover, usually due to faulty hardware drivers or critical memory corruption. The most effective way to diagnose these events is to examine the resulting dump files, which provide a snapshot of the system state at the moment of the crash. Windows mini-dump files can be analyzed with tools like WinDBG, while Linux kernels generate logs and core dumps that reveal why a panic was triggered. By examining the stack trace, we can often identify the specific module or driver responsible for the failure and decide whether to update, remove, or roll back that component. Service startup failures and dependency chains represent a frequent, yet often overlooked, category of software issues. A service may fail because it requires another service that is either disabled, crashed, or currently in a hung state. When debugging such failures, we must inspect the service configuration to identify its dependencies and verify the status of each requirement. If a dependency is missing, resolving the issue involves correcting the service registration or ensuring the necessary environment variables are set correctly during the startup sequence. This systematic approach of verifying the hierarchy of services prevents us from wasting time on the incorrectly identified service when the root cause resides several layers deeper in the boot chain. Registry corruption in Windows or localized file corruption in system libraries can degrade system performance or render it entirely unusable. The System File Checker, or SFC, is designed to scan protected system files and replace corrupted variations with verified copies from the local store. When SFC is insufficient, the Deployment Image Servicing and Management Tool, or DISM, provides a more robust mechanism to repair the underlying system image itself. In a Linux context, File System Integrity Checks, or FSCK, serve a similar purpose by finding and repairing inconsistencies in the file system structure. Ensuring the integrity of the operating system files is a fundamental task that must precede any higher-level troubleshooting efforts. Performance bottlenecks often originate from rogue processes consuming an excessive share of CPU cycles or available memory. To identify these culprits, we utilize built-in performance monitors or command-line utilities like top and top to observe real-time resource utilization. Once a process is identified as the source of the contention, we evaluate whether it should be terminated, reconfigured, or optimized to restore balance to the system. Analyzing the duration of these spikes often reveals whether the problem is related to regular batch jobs, memory leaks within an application, or unauthorized software activity. Maintaining this visibility into process behavior is critical for ensuring that capacity plans align with actual runtime demands. Patch management is a vital operational procedure, yet updates occasionally introduce compatibility issues or broken dependencies. When a server becomes unstable following the deployment of a patch, the first course of action is usually to roll back the update to restore the previous known good configuration. This process highlights the necessity of maintaining robust system backups and snapshots before performing any update operations. Once the system is stabilized, we must inspect the logs and update documentation to determine why the patch failed, perhaps identifying conflicts with existing legacy applications. By standardizing the rollback procedure, we transform a critical incident into a controlled administrative task. Diagnostic logging provides the necessary evidence to move from guessing to knowing when investigating system errors. In Windows, the Event Viewer centralizes information across application, security, and system logs, allowing us to correlate timestamps with reported issues. Linux administrators look to the syslog service, where information is directed to files such as /var/log/messages or /var/log/syslog, depending on the distribution. When reviewing these logs, look for patterns that precede the failure, such as specific error codes or repeated attempts to initialize hardware. This evidence-based approach is exactly what professional system administration entails. Permissions issues, whether governed by NTFS access control lists or POSIX modes, frequently masquerade as software malfunctions. If an application cannot write to a configuration file or access a dependency library, the result is often a cryptic error message that suggests a code defect when the fault is purely administrative. Verifying the effective permissions on a file or folder involves checking both user membership and specific access grants to ensure proper reach. By applying the principle of least privilege, we secure the server while ensuring that required services have the necessary access to function correctly. Hardware abstraction layer issues and driver conflicts typically arise when there is a mismatch between the software and the underlying physical or virtual hardware. If a driver update breaks system stability, rolling back to the previous version is the quickest path to resolution through device management consoles. In scenarios where the OS is completely inaccessible due to these problems, booting into safe mode or single-user mode allows us to perform repairs without loading non-critical drivers or external services. These modes essentially provide a minimal operating environment, stripping away complexity so that we can correct the configuration error or remove the offending driver directly. See you in the next lecture. Welcome back to our exploration of server administration, where we now turn our focus to the complex landscape of network and connectivity troubleshooting. In this discussion, we will methodically examine how to isolate and resolve network failures, moving systematically from the physical layer up through the application stack. Troubleshooting connectivity often begins at the physical layer, which is deceptively simple until you encounter silent failures like port flapping or intermittent signal loss due to degraded cabling. When a link light blinks irregularly or a port constantly cycles between up and down states, verify the patch cable integrity and examine the physical switch port for signs of physical damage or excessive heat. Layer 1 issues are binary in nature, yet they often manifest as complex application errors, leading many administrators to hunt for software bugs when the problem is merely a crimped Ethernet cable. Beyond physical infrastructure, VLAN mismatches and misconfigured trunking ports frequently manifest as partial connectivity, where a server can reach its gateway but lacks access to specific subnets. You must ensure that the switch port profiles strictly align with the server's virtual or physical NIC tagging requirements, as any discrepancy here effectively partitions the server from the intended broadcast domain. Moving upward into the network layer, IP address conflicts and DHCP exhaustion represent common but avoidable service disruptions that directly impact server availability. Conflict detection usually occurs when a static IP is erroneously assigned to a device already managed by a DHCP scope, causing intermittent network drops for both affected nodes. DHCP exhaustion, on the other hand, occurs when the pool of available addresses is smaller than the number of active requests, a situation that often necessitates either extending the lease duration or increasing the subnet mask to allow for more host addresses. Always utilize command line tools like ping for basic reachability tests, but remember that a successful ping only indicates that ICMP is allowed and the route is valid, not that the application service is healthy. For more granular investigation, tools like traceroute or tracert provide a hop-by-hop view of the path, which proves invaluable when identifying routing loops or incorrect gateway configurations that keep packets trapped within a local network segment. Name resolution failures often masquerade as network outages, yet they are strictly application-level concerns involving the DNS hierarchy. When users or services cannot resolve a hostname, the first step is to query the DNS server directly using nslookup or dig to see if the record exists and if the server responds in a timely fashion. Furthermore, cache poisoning or stale records can lead clients to incorrect IP addresses, necessitating a purge of the local or server-side cache to force a fresh lookup. While DNS governs identity, SSL/TLS certificate issues often cause encrypted connections to be dropped immediately, appearing as a connectivity error to the uninitiated. A common pitfall is a certificate expiration or a mismatch between the common name on the certificate and the FQDN accessed by the client, which requires rigorous verification of the certificate store and the chain of trust on the server. When basic connectivity is restored, performance issues like slow throughput and high latency require a more analytical approach, often necessitating the use of packet captures. Capturing traffic with Wireshark allows you to inspect the TCP handshake process, where you might uncover retransmissions, window size issues, or handshake delays that point to congestion or packet loss. You should also regularly inspect the MAC tables on your switches and the ARP tables on your servers to ensure that frame and packet mapping remains accurate and that there is no spoofing or unexpected broadcast traffic flooding the network. This involves navigating the CLI of your networking equipment to verify that the switch is actually learning the correct port for a given MAC address. Without these diagnostic foundations, performance tuning is merely guesswork. By leveraging NetMap or similar tools for network auditing, you gain the visibility required to make data-driven infrastructure decisions. Virtualization adds another layer of abstraction, where vSwitch configuration errors or misconfigured port groups on a hypervisor can silently drop traffic despite the physical hardware appearing healthy. You must evaluate the virtual switch topology just as you would physical hardware, checking for tagged VLAN traffic that isn't reaching the guest machines due to an incorrectly configured virtual uplink. Firewall misconfigurations are equally common, as rules designed to harden the server might inadvertently block legitimate traffic protocols required for back-end communication or service interdependencies. Before assuming a network failure, perform a targeted analysis of the firewall logs to see if packets are being dropped by a default deny rule, which is a frequent culprit when introducing new services or changing port requirements. Establishing a baseline for what constitutes normal traffic allows you to identify these anomalies quickly, ensuring that you resolve the root cause rather than just applying a temporary fix. See you in the next installment. Welcome back. In this session, we will examine the systematic recovery processes required when storage subsystems encounter failure or performance degradation. Dealing with RAID array degradation requires a methodical approach that prioritizes data integrity above raw speed. When a drive in a redundant array fails, the system transitions into a degraded state, continuing to operate while utilizing parity or mirroring to reconstruct missing blocks for incoming read requests. The most immediate concern here is the unrecoverable read error, or URE, which can occur during the rebuild process when the controller attempts to read the remaining healthy disks to calculate the missing data. If another drive suffers a fault during this period of high stress, the entire array may become inaccessible, rendering the data lost. Consequently, the first step in any recovery procedure is ensuring that current, consistent backups are available before attempting to hot swap a drive. Once the physical replacement is slotted, the controller typically initiates an automatic rebuild, though an administrator must often manually trigger or prioritize this process through the storage management console. Controller failures represent a more systemic issue than a simple drive replacement, as they often lead to configuration metadata loss. When you replace a controller, the new hardware might not immediately recognize the existing virtual disks because the volume metadata is stored on the disks themselves rather than being hard-coded into the controller firmware. In this scenario, we must look for a foreign configuration import option within the RAID utility, which directs the controller to scan the attached disks for valid metadata headers and map the volume structures accordingly. Conversely, troubleshooting a SAN environment involves deeper abstraction layers like LUN masking and mapping, which restrict or grant access to specific storage volumes based on the host bus adapter or iSCSI IQN. If a host suddenly loses visibility to its storage, it is prudent to first verify that the zoning and masking policies have not been inadvertently altered during an infrastructure update. Connectivity issues, particularly concerning iSCSI, often originate from authentication mismatches rather than physical network failure. When a server fails to connect to a target, we should verify the challenge handshake authentication protocol credentials, ensuring that the secret configured on the iSCSI initiator matches the entry on the target side. If credentials and routing are verified, we must inspect the multipathing software, which might be struggling to manage path failovers or persistent reservations. In cases where the file system itself is the source of the problem, such as corruption induced by a power cut, we rely on low-level utilities like FSCK or checkdisk to repair metadata inconsistencies. These tools are powerful but potentially destructive if run on a live, mounted volume, so they must be treated as a recovery option of last resort after verifying that the underlying block storage is healthy. Managing capacity and performance requires balancing IOPS limits against the physical constraints of the storage media. A disk full condition is an administrative failure that often impacts log truncation and snapshot management. Failing to clear outdated snapshots can result in a performance gridlock where the file system becomes read-only. Furthermore, storage alignment issues, where the file system clusters do not correspond to the physical disk sectors, can lead to significant write amplification and latency. Such performance bottlenecks are frequently misunderstood as disk failure when, in reality, they are symptoms of inefficient I/O pathing or over-provisioned IOPS limits. By monitoring these metrics closely and ensuring that garbage collection cycles have enough headroom to operate, we create a resilient storage architecture that can survive the common stresses of an enterprise environment. See you in the next lecture. Welcome back. Today we are shifting our focus to the practical realities of security incident response and server monitoring. We will cover the identification of threats, incident containment strategies, and the post-incident procedures necessary for maintaining a hardened environment. Identifying a security breach often begins with subtle deviations from established operational norms, which is why baseline monitoring is not just a best practice, but a necessity. You must look for unauthorized accounts appearing in your directory services, as these are often indicators of persistent access attempts or compromised credentials. Similarly, unusual log entries, such as off-hours logins from unusual geographic locations or repeated access denials to sensitive configuration files, should trigger immediate scrutiny. Spikes in outbound traffic are perhaps the most telling signs of a potential exfiltration event or a server being utilized as a botnet node. When you notice anomalies in network telemetry, you should correlate this data with local host logs to determine if the traffic originates from an authorized process. Troubleshooting authentication failures requires a disciplined approach, specifically examining account lockout logs to discern between legitimate human error and automated brute force attacks. System administrators often overlook the relationship between these authentication failures and broader security trends within their environment. By systematically reviewing these indicators, you can distinguish between routine configuration errors and targeted security compromises. Once you suspect a breach, the focus shifts to containment and investigation, particularly regarding malware infections and privilege escalation. If you identify a malware infection, the immediate goal is isolation to prevent lateral movement while preserving the evidence for forensic analysis. This often involves segmenting the affected server from the network or placing it into a constrained virtual environment before attempting remediation. Analyzing audit logs for privilege escalation is critical. You are looking for unexpected changes in group memberships or the execution of binaries with elevated permissions that do not align with job functions. In these scenarios, you must verify that your firewall and intrusion detection or prevention systems are actually providing the expected coverage rather than just generating noise. Effective security monitoring often hinges on utilizing security information and event management systems, or SIEM, to correlate disparate log events into a single, cohesive timeline of activity. This aggregation allows you to connect a failed login attempt on one system with suspicious command line activity occurring on another. Infrastructure security extends to the integrity of your PKI and the resilience of your server cluster against volumetric denial of service attacks. Troubleshooting certificate-based access often involves verifying the certificate revocation list, or CRL, to ensure that valid clients are not being denied service due to expired or incorrectly flagged certificates. When facing a potential denial of service or distributed denial of service attack at the server level, your primary objective is to maintain availability for legitimate users while discarding malicious packets. This may involve adjusting connection timeouts, implementing rate limiting on network interfaces, or coordinating with upstream providers to filter traffic based on malicious signatures. Beyond the digital realm, you must ensure that physical security breaches are documented with the same level of rigor as their digital counterparts, including tracking unauthorized attempts to access server racks or console ports. Without detailed documentation, you lack the information necessary to satisfy regulatory compliance requirements, which often mandate specific reporting intervals for security incidents. Recovery and post-incident analysis are the final stages that transform an unfortunate event into an opportunity for improved infrastructure resilience. Restoring from a known good baseline configuration, often referred to as a gold image, is the standard for returning a compromised system to a trusted state. This process eliminates the inherent risk of hidden persistence mechanisms, such as rootkits, that might bypass standard file-level cleaning. However, simply restoring a system is insufficient if you do not conduct a thorough post-incident analysis to identify the root cause of the breach. This involves reviewing your logs to trace the entry vector and verifying if existing security policies were enforced correctly or if they were inadequate for the threat encountered. You must document these findings comprehensively to refine your security stance, as the goal is not just recovery, but the permanent prevention of similar recurrence. By maintaining a continuous feedback loop between security operations and your hardening protocols, you decrease your attack surface over time. This iterative process is what defines a mature and defensible server management strategy. See you in the next lecture. Welcome back to our technical journey through the Server Plus domain, where we turn our attention toward the practical realities of managing virtualized infrastructures. Today, we focus on identifying and resolving the specific performance bottlenecks inherent in virtual and cloud environments. In a virtual environment, resource contention often manifests in ways that defy traditional physical server diagnostics. When you observe high CPU ready time or wait time, you are witnessing the hypervisor delaying a virtual machine from executing its instructions because the physical CPU cores are already saturated by other guests. This is the hallmark of the noisy neighbor effect, where a single resource-intensive workload disproportionately affects the performance of others sharing the same underlying hardware. To mitigate this, you must analyze performance metrics across the cluster to determine if specific VMs are consistently over-provisioned or if the host is simply undersized for the total aggregate demand. Right-sizing requires a careful look at historical utilization data rather than relying solely on peak spikes, which can often be misleading if they occur only during infrequent batch processes. Memory management in virtualized hosts introduces the risk of swapping and paging, which are far more destructive to performance than they would be on a bare metal machine. When a hypervisor runs low on physical memory, it may force guest operating systems to swap to their virtual disks, creating a cascading performance degradation that is difficult to isolate. You should always verify that memory overcommit ratios are within acceptable thresholds for your specific workload types, as databases require predictably low latency that swapping effectively destroys. Simultaneously, monitor disk I/O bottlenecks that often result from excessive virtual disk contention on the same physical storage fabric. If your storage backend lacks sufficient IOPS, even the fastest virtualized CPU will remain idle, waiting for data to arrive from the underlying LUNs or volumes. Connectivity between VMs often relies on virtual switches, which act as the layer 2 bridge for guest traffic within a host. When VMs cannot communicate, start by investigating the port group assignments, virtual LAN tagging, and security policies that might be dropping traffic before it exits the host's virtual switch. If the problem involves moving workloads between hosts via technologies like vMotion, the primary culprits are usually CPU feature mismatches or underlying network latency between the source and destination hosts. You must ensure that the CPU compatibility masks are properly configured in your cluster settings to prevent migration failures. Furthermore, snapshot management is a frequent source of performance decay. When snapshot chains grow too long or fail to consolidate correctly, disk I/O increases exponentially, eventually leading to potential data corruption or severe host-level instability. Cloud connectivity adds another layer of complexity when bridging your on-premises infrastructure to IaaS providers. Whether you utilize site-to-site VPN tunnels or dedicated circuits like Direct Connect, packet loss and latency are the prime enemies of consistent application performance. You need to monitor these connections for throughput fluctuations and ensure that your local routing tables are correctly propagating routes to the cloud environment. Clock synchronization is another subtle but critical factor. Virtual machines are notorious for experiencing clock drift when the hypervisor fails to present an accurate time source. This drift can cause issues with Kerberos authentication, audit logging, and database consistency, so always configure the host to act as a reliable NTP source for its child virtual instances. Container orchestration presents unique challenges, particularly regarding the persistence of storage and the ephemeral nature of the workloads. When containers fail to mount volumes correctly, you must verify the underlying storage driver configuration and the permissions assigned by the orchestration engine. It is rarely the application code itself that is at fault during these mounting failures. Rather, it is often a misconfiguration in the CSI driver or the network path between the cluster nodes and the storage array. As you investigate these failures, consider the abstraction layers involved: the container, the pod, the node, and finally the storage provider, to isolate exactly where the handshake is breaking down. A methodical approach, moving from the most abstract layer downward to the physical transport, remains the most effective way to restore service in these dynamic, software-defined environments. See you in the next session. Welcome back. We are turning our attention to performance tuning and capacity planning to ensure our infrastructure remains scalable and reliable. Performance tuning is not merely about chasing higher clock speeds or adding more memory. It is an analytical discipline rooted in observing long-term trends. By establishing a robust performance baseline, you gain the ability to distinguish between normal operational variations and genuine anomalies that signal an impending failure. We will examine how to leverage diagnostic utilities like Perfman on Windows or Top and Iostat on Linux to capture these essential metrics. When you observe consistent growth in CPU utilization or memory consumption over time, this data serves as the foundation for your hardware upgrade lifecycle planning. Proactive replacement of aging components should always be driven by these documented trends rather than reactive emergency repairs. Integrating this long-term perspective into your administrative workflow prevents unexpected downtime and optimizes your hardware investment. Effective capacity planning requires a deep understanding of where your specific bottlenecks reside, particularly within the I/O subsystem. Applications that rely heavily on disk operations often suffer when spindles cannot keep pace with request volume, necessitating a transition to flash storage or the implementation of smart caching layers. We must also consider the overhead introduced by encryption and compression, as these security and data management features impose a measurable load on system resources. Balancing this against the performance per watt metric allows you to build a greener, more cost-effective server room. If your throughput remains constrained despite storage optimization, investigate your network configuration for congestion that might indicate a need for increased bandwidth or hardware upgrades. Ultimately, tuning OS parameters, such as adjusting file system journaling or network stack buffers, serves to specifically tailor your OS behavior for either high-transaction databases or high-concurrency web services. To maintain stability under high demand, scaling strategies must be baked into your architectural design. Horizontal scaling, which involves adding more server instances to distribute the load, is almost always more sustainable than attempting to infinitely scale a single monolithic server vertically. Utilizing load balancing to distribute incoming traffic ensures that no single point of infrastructure becomes a bottleneck, thereby improving overall response times. In shared environments, implementing resource limits and quotas is an essential practice to prevent a single noisy neighbor from starving other applications of CPU or memory cycles. Managing these constraints properly forces your applications to operate within predictable boundaries, simplifying capacity planning significantly. You are essentially shifting the goal from raw maximum performance to predictable, consistent performance under a wide variety of load conditions. This systematic approach to tuning and planning ensures your servers consistently meet organizational demands without unnecessary expenditure. I will see you in the next lecture. Welcome back. In this session, we will examine the critical administrative structures that keep modern data centers organized, secure, and legally compliant. Change management is not merely an administrative hurdle. It is the primary defense against self-inflicted downtime. When you introduce a change request, or RFC, you are initiating a formal process intended to assess risk, impact, and compatibility before a single command is executed. Once the request is documented, it must be reviewed by a Change Advisory Board, or CAB, which serves as the cross-functional brain trust for the organization. This body evaluates whether the proposed change aligns with business needs and, perhaps most importantly, whether a viable rollback plan exists. A rollback plan is your insurance policy, detailing the specific steps required to revert the system to its previous known good state if the deployment fails. Without this structured approach, an environment quickly drifts into an unmanageable state where technical debt accumulates in silence. Effective asset management relies on the integrity of your configuration management database, or CMDB, which acts as the single source of truth for your infrastructure. This system allows you to map interdependencies, helping you understand exactly which business services will suffer if a specific database server fails or requires patching. You must also maintain rigorous inventories of both hardware and software, ensuring that your license counts for operating systems and applications match your actual deployments. If you fail to track these assets, you risk license non-compliance, which can lead to severe financial penalties during an audit. Asset tracking also extends to the lifecycle management of hardware, mapping the journey from procurement and initial deployment to ongoing maintenance, and finally, secure disposal. By treating hardware and software as trackable lifecycle objects, you ensure that you are never paying for shelfware or running end-of-life hardware that is no longer supported by vendors. Documentation is the silent partner of every professional administrator, yet it is often the first thing neglected under pressure. Your environment should have up-to-date logical and physical network diagrams that define how traffic flows through your switches, firewalls, and server racks. Beyond diagrams, sitebooks should contain granular details about IP schemas, server naming conventions, and consistent asset tagging protocols. When you formalize your server naming and tagging, you immediately reduce the cognitive load on your team during incident response scenarios. Furthermore, maintenance windows and scheduled downtime must be recorded and communicated through predetermined notification channels to maintain trust with stakeholders. By adhering to these documentation standards, you transform your infrastructure from a collection of pet servers into a predictable, reproducible service delivery platform. Finally, managing the intersection between your infrastructure and external agreements is vital for operational stability. Service-level agreements dictate the expected uptime and response times for your business services, serving as the benchmark for your performance monitoring. You must align these internal SLAs with the support contracts provided by your hardware and software vendors to avoid gaps in coverage. If a kernel-level bug crashes your server, you need to know exactly which vendor support contract applies and what the terms of their response obligation are. Viewing vendor relationships through the narrow lens of a contract ensures that you are always operating with clear expectations regarding support and resolution timeframes. Consistency in these administrative habits is exactly what separates a reactive firefighter administrator from a proactive professional who manages systems with deliberate architectural intent. I will see you in the next lecture. Welcome back. In this chapter, we explore the critical domain of environmental controls and the physical safety measures required to maintain long-term server infrastructure stability. Managing the physical environment of a data center is fundamentally an exercise in risk mitigation and lifecycle preservation. The ASHRE guidelines provide the industry benchmark for operating environments, typically recommending a temperature range between 18 and 27 degrees Celsius or 64 to 81 degrees Fahrenheit to ensure optimal hardware longevity. While modern servers are slightly more resilient than their predecessors, maintaining stable humidity levels is equally critical to prevent electrostatic discharge or, conversely, corrosion and condensation issues. Relative humidity should generally be kept between 40 and 60%. When an HVAC system fails, your immediate concern shifts to thermal management until repairs are completed, which often involves temporary rack-level ventilation or localized portable cooling units. You must monitor these fluctuations closely, as rapid thermal cycling can be just as damaging to components as operating consistently beyond recommended thresholds. Treating air quality and thermal consistency as a foundational architectural requirement is the first step toward high availability. Fire suppression is another area where standard office solutions are often inadequate, necessitating a move toward specialized gaseous or dry pipe systems. Wet pipe systems remain pervasive in many buildings, but in a server room, water is rarely your friend due to the catastrophic risk of shorts and terminal equipment damage. Dry pipe systems offer a safer alternative by ensuring water only enters the pipes upon activation, reducing the risk of accidental leaks above your racks. However, clean agent systems like FM200 or Energen represent the gold standard for high-security environments. These substances function by interrupting the combustion process at a molecular level or displacing oxygen without leaving behind the residue associated with traditional chemicals or water. It is essential that these systems integrate directly into your facility's safety controls to ensure they are serviced according to local fire codes and manufacturer specifications. Power management serves as the backbone of every uptime guarantee, and this begins with redundant utility feeds to ensure no single point of failure at the power grid level. An uninterruptible power supply is your first layer of defense, intended not for long-term operation, but as a bridge to allow graceful shutdowns or activation of backup generators. Maintenance of these units must be rigorous, involving periodic battery load testing to ensure capacity has not degraded beyond usable limits. Generators must also undergo regular testing under load to confirm that they will indeed start and sustain the required power draw when the primary utility feed oscillates or fails completely. Alongside these systems, the emergency power off button is a critical, yet hazardous, interface that requires strict physical protection. Accidental activation can cause immediate, massive downtime, so you must install protective covers and educate all staff on the exact protocols for when and how that button should be triggered. Physical security and workspace safety round out the environmental requirements, emphasizing that an inaccessible data center is fundamentally more secure. Auditing access logs and enforcing strict visitor policies ensures that you maintain a clear chain of custody for anyone entering the restricted zone. Within the racks themselves, proper cable management is not merely an aesthetic preference but a vital safety and maintenance protocol. Poorly organized cables block airflow, increase ambient heat, and make troubleshooting near impossible when time is of the essence. You should always implement a clear labeling standard that maps each connection to its destination, allowing you to manipulate hardware without disturbing unrelated live circuits. Grounding and bonding of your racks and cabinets are similarly non-negotiable. This completes the electrical circuit for fault currents and serves as a vital protection against electrostatic buildup that could damage sensitive silicon components over time. Safety procedures extend to the physical interaction between personnel and the equipment, where simple human error remains a primary cause of downtime. Heavy lifting techniques are essential when moving servers or auxiliary hardware, as improper posture is a liability for both the technician and the integrity of the equipment. Rack tipping is a realistic danger during installation or maintenance, making the use of anti-tip stabilization kits mandatory whenever you slide a heavy chassis out on rails. Documentation is your most important tool in these scenarios, specifically the material safety data sheet collection, which provides necessary information on any hazardous materials present in the facility, such as battery components. Furthermore, managing the ambient noise and lighting levels is a matter of ergonomics, as extreme acoustic levels can indicate mechanical distress while poor lighting inevitably leads to mistakes when working behind darkened server rows. Maintaining an environment that respects both the hardware and the human element is the definition of operational maturity. I will see you in the next lecture. Welcome back to our exploration of server administration. In this session, we will discuss the essential maintenance practices required to ensure long-term server reliability and performance. Physical maintenance is often overlooked, yet it remains the primary defense against premature hardware failure. Dust accumulation within chassis intakes and exhaust ports creates an insulating layer that traps heat, forcing internal fans to work harder and eventually fail. You must establish a routine schedule to inspect fan health, listening for bearing noise or monitoring RPM speeds through the baseboard management controller. While performing these inspections, it is a sound practice to verify that all physical power and data connections are firm, as heat cycling can cause cables to gradually migrate out of their seated positions. Ignoring the physical health of a server often leads to intermittent bus errors or thermal throttling that proves exceptionally difficult to diagnose via software alone. A systematic approach to physical cleaning and connection integrity directly extends the mean time between failures for your production hardware. Digital maintenance is equally critical, centering heavily on the life cycle of firmware and OS patches. Establishing a robust patch cycle requires a balance between vulnerability management and system stability, which is why testing updates in a staging environment is non-negotiable. When addressing firmware updates for motherboards, RAID controllers, and network interface cards, you should always consult the vendor's release notes for specific dependencies. Bricking a RAID controller due to a mismatched firmware version is a common operational failure that you should actively avoid through careful planning. Furthermore, log management deserves dedicated attention to prevent disk exhaustion, which can cripple a server faster than any virus. By implementing automated log rotation and aggregation to centralized management systems, you ensure that you have access to historical security logs and performance reports without sacrificing operating system stability. Data integrity and power management form the backbone of a resilient server environment, requiring proactive validation rather than passive reliance on alerts. Backup integrity is only as strong as your last successful test restore, meaning you must periodically perform full recovery exercises to verify that your data is not just present, but usable. Similarly, UPS batteries have a finite chemical lifespan, and their capacity degrades even when they are not actively discharging. You should schedule regular battery health checks and controlled load tests to ensure that the UPS can actually bridge the gap during a power failure. If a battery unit fails its load test, it must be replaced immediately to protect the server's underlying electronic components from unexpected voltage drops or sudden shutdowns. The end of a server's life requires the same level of discipline as its commissioning, particularly concerning data sanitization. When hardware is decommissioned, you must ensure that sensitive information is rendered irrecoverable through professional wiping or drive shredding, in accordance with your organization's security policy. Following the physical destruction of storage media, the remaining chassis components should be processed through certified e-waste recycling programs to meet environmental compliance standards. Throughout every stage of the life cycle, from deployment to decommissioning, you must update your documentation to capture every significant change. Relying on tribal knowledge is a recipe for disaster, whereas maintaining a centralized repository ensures that any administrator can take over a system with a clear understanding of its current configuration. Finally, modern server environments should leverage out-of-band management and infrastructure as code to maintain consistency. Security for out-of-band management interfaces, such as ILO or iDRAC, is paramount. These interfaces must reside on isolated management networks and utilize strong, multi-factor authentication to prevent unauthorized remote access. To achieve true consistency, move away from manual configuration toward infrastructure as code practices. By defining your server environments in version-controlled scripts, you can reliably reproduce a server setup from scratch, eliminating the configuration drift that plagues manual administrative workflows. This shift in methodology not only improves transparency but also drastically reduces the probability of human error during system updates. See you in the next lecture. Welcome back. Today we will discuss the practical implementation of server security policies to ensure your infrastructure remains resilient against evolving threats. In this session, we will explore the foundational administrative controls and procedural frameworks required to maintain a secure server environment. Developing and enforcing an acceptable use policy is the cornerstone of any organizational security posture, as it clearly defines the expectations for system interaction. You must ensure that users and administrators understand the boundaries of acceptable behavior, which inherently minimizes the risk of insider threats or accidental compromise of sensitive systems. Complementing these policies are robust identity controls, specifically password complexity and rotation requirements that enforce strong authentication hygiene across your user base. Account lockout policies serve as an essential deterrent against brute force attacks by limiting the number of unsuccessful login attempts before an account is disabled. Furthermore, implementing banner warnings provides a legal notice to any individual accessing the system, confirming authorization and reminding them that unauthorized activity is subject to monitoring. These seemingly simple measures act as a deterrent and demonstrate administrative diligence when managing server environments. Data classification dictates how information is stored, processed, and transmitted, necessitating rigorous handling procedures based on the sensitivity of the data involved. For instance, public, internal, and confidential data require distinct protection mechanisms, such as encrypted storage or restricted access controls, to maintain integrity and confidentiality. Disaster recovery policies must be regularly updated to reflect changes in your technical environment, while stakeholder communication plans ensure that all relevant parties understand their responsibilities during an emergency. Security training is not a one-time event. It must be a persistent effort for all technicians to ensure they remain cognizant of modern attack vectors and remediation strategies. By fostering a culture of continuous learning, you reduce the likelihood of human error, which remains a primary entry point for attackers in most enterprise systems. Hardening is the intentional process of reducing the attack surface by disabling unnecessary services and configuring the operating system to a known secure state. Utilizing standards such as CIS benchmarks or STIGs provides a repeatable, verifiable method to ensure your servers adhere to industry best practices rather than relying on guesswork. Beyond digital hardening, physical access controls and meticulous visitor logging remain imperative for protecting the underlying server hardware from tampering or theft. Managing third-party vendor access is equally critical, as supply chain vulnerabilities often manifest through overly permissive or forgotten credentials granted to external contractors. You must regularly audit these access points to ensure they follow the principle of least privilege while maintaining an accurate inventory of who has authorized access into your production facility. Regulatory compliance frameworks like HIPAA, PCI DSS, and GDPR are not merely bureaucratic requirements but are structured approaches to securing data storage and processing pipelines. When managing servers, you are responsible for documenting that your configuration and data handling methods align with the specific mandates of your industry. This involves not only setting technical controls but also performing periodic internal vulnerability scans and executing penetration tests to validate that your defenses hold up against realistic threats. If a scan reveals a vulnerability, it must be integrated into your patch management workflow, ensuring that the remediation is tracked, validated, and documented. Maintaining this level of rigor ensures that you are consistently prepared for external audits and, more importantly, that your operational security is effective in preventing unauthorized access. By systematically applying these policies, you move from a reactive security stance to a proactive posture that aligns with enterprise-grade standards. The goal is to create a predictable, defensible, and well-documented server environment where security is integrated into every stage of the lifecycle. As you move forward, keep in mind that the effectiveness of these policies relies heavily on your ability to enforce them consistently across all facets of your infrastructure. Diligent documentation and regular review cycles will help you maintain compliance and security integrity over the long term. I will see you in the next lecture. Welcome back. In this lesson, we will examine the critical infrastructure that keeps your servers running, power delivery and management strategies. To understand data center power, we must distinguish between single-phase and three-phase power. Single-phase power is ubiquitous in residential environments, utilizing two wires to deliver a voltage that oscillates in a single sine wave. In contrast, three-phase power delivers three overlapping alternating currents, which provides a more consistent flow of electricity that is significantly more efficient for high-density server racks. Large-scale server deployments almost exclusively rely on three-phase power because it allows for thinner wiring and reduced copper usage while delivering the same energy load. When planning your server room, you will often need to convert this three-phase input into single-phase outputs at the rack level using power distribution units. Understanding this distinction is fundamental to calculating your facility's electrical capacity and preventing thermal overload on your circuits. Always ensure your power delivery strategy accounts for the specific power requirements of your hardware density. Server reliability often hinges on redundancy, which we achieve through redundant power supply units and independent circuits. A single server with two PSUs is a classic example of fault tolerance, but its effectiveness depends on how those PSUs are configured. In a load balancing configuration, both units work simultaneously to share the power burden, which can increase the efficiency of the units, but it also means that both are under constant stress. Conversely, a failover configuration keeps one PSU as a standby that only activates if the primary unit ceases to function. For true redundancy, you must plug these PSUs into separate power circuits, preferably fed by different uninterruptible power supplies or independent grid feeds. This approach protects your infrastructure against a single blown circuit breaker or a faulty outlet strip taking down your entire compute node. When selecting a UPS, you have three primary architectural choices: standby, line interactive, and double conversion. Standby UPS systems offer the most basic protection, remaining idle until a power loss occurs, at which point they switch to battery power, creating a momentary gap in delivery. Line interactive systems are more robust, as they include an auto-transformer to correct minor voltage fluctuations without draining the battery. Double conversion, or online UPS systems, are the industry standard for enterprise servers because they convert incoming AC power to DC and then back to AC. This constant regeneration ensures that sensitive server components receive a perfectly clean, reconstructed sine wave regardless of the condition of the utility power. Double conversion units are the only choice for mission-critical applications where even a millisecond of fluctuation is unacceptable. Capacity planning requires an accurate calculation of power requirements in both watts and voltamps. While watts represent the actual power consumed by the server, VA represents the apparent power, which is critical for sizing UPS and PDU capacity because it accounts for power factor inefficiencies. When you deploy a rack, you must sum the VA ratings of every piece of equipment to ensure the PDU does not trip during peak operational cycles. Beyond electricity, you must also consider cooling, which is directly proportional to power consumption. Every watt consumed by a server is ultimately converted into heat, requiring roughly 3.41 BTU per hour per watt of energy used. You should design your HVAC systems based on these thermal output metrics rather than just relying on the physical size of the room. Managed PDUs and automatic transfer switches are essential tools for remote diagnostics and hardware flexibility. A managed PDU provides the ability to cycle power to individual outlets, allowing you to perform hard reboots on unresponsive servers from a remote location. If you have legacy servers that only feature a single power cord, an automatic transfer switch is the bridge to redundancy you need. It monitors the power state of your primary source and near instantaneously switches to a secondary input if a failure is detected. When integrating backup generators, ensure you have a regular maintenance schedule that includes load banking the generator to prevent fuel degradation. Routine testing of these failover systems is not optional. You must simulate power outages to confirm that your transition protocols function as documented in your disaster recovery plan. Finally, you must actively monitor your power quality to ensure the longevity of your server components. Issues such as voltage sags, brownouts, and surges can wreak havoc on sensitive internal components, leading to premature hardware failure or subtle, difficult-to-diagnose data errors. Implementing robust surge suppression and maintaining a clean power environment effectively hedges against these environmental risks. By combining these management strategies with diligent performance monitoring, you ensure that your hardware remains both durable and dependable. Maintaining high power quality is an investment in the overall health of your entire data center architecture. I look forward to our next session together. Welcome back. In this lecture, we will explore the critical role of documentation within the server environment and how standard operating procedures maintain system integrity and operational efficiency. Standard operating procedures, or SOPs, are far more than just bureaucratic formality required by some distant management layer. When you are standing in the middle of a high-pressure server recovery event or dealing with an escalation at 3 in the morning, the quality of your documentation is the primary variable that determines whether you solve the problem or exacerbate it. A well-constructed SOP for tasks like server provisioning or backup restoration acts as an externalized memory buffer, removing the cognitive load of remembering specific configurations or dependency sequences. When we document user onboarding, we ensure that every identity is provisioned with consistency and security, which is often the first line of defense against privilege creeping. These documents should treat the technical process as a deterministic chain of events where every state change is explicitly accounted for. By prioritizing clarity, we transform tribal knowledge into a reproducible asset that any skilled engineer can execute without hesitation. Runbooks for disaster recovery occupy a unique position in our documentation architecture because they are intended for the most volatile situations imaginable. While a standard procedure describes how to perform a routine task, a runbook must provide a survival guide for catastrophic failure, necessitating a level of detail that covers prerequisites, validation checks, and specific branching logic. Good technical writing here means avoiding ambiguous language like verify the server is running and replacing it with concrete proofs like confirm the presence of the service PID or verify a successful response to a local HTTP probe. Incorporating relevant screenshots is not just helpful for non-experts. It provides a visual reference that allows a stressed operator to quickly orient themselves within an unfamiliar console interface. Maintaining this documentation under version control is non-negotiable because it allows us to track why specific decisions were made and enables us to roll back to a previously functional procedure if an update inadvertently introduces errors during active recovery. The creation of a centralized knowledge base serves as the foundational layer for managing repeating issues that naturally occur in complex distributed environments. If your team spends time resolving the same database connection timeout or disk latency bottleneck repeatedly, you have failed to institutionalize the solution, effectively taxing your team's productive capacity. By ensuring that these resolutions are indexed and searchable, you enable a culture of self-service that liberates your senior staff from performing repetitive support tasks. This shift in focus is essential for evolving from reactive firefighting toward a more manageable service management structure, which is a core tenet of the ITIL framework. When we discuss onboarding and offboarding for your fellow IT staff, proper documentation ensures that the tribal knowledge required to maintain these specialized systems does not vanish the moment someone resigns from their position. Custom scripts and automation workflows represent the pinnacle of modern server management, yet they are frequently left poorly documented until they break in production. When you write a script, you must include a header that defines its purpose, the required environment variables, and the expected state transitions. Otherwise, your future self or your colleagues will struggle to comprehend the intention behind the logic. This documentation should be living alongside your code, preferably maintained within the same repository to ensure that code changes and manual updates are synchronized. Furthermore, you must maintain a clear, updated contact list for both internal escalations and external vendor support to avoid losing time during an outage searching for the right phone number. Remember that this contact information, along with your SOPs and runbooks, constitutes sensitive data that must be protected by robust encryption at rest and strict identity-based access control. See you in the next lecture. Welcome back, and let's dive into the practical realities of infrastructure automation. In modern server environments, manual intervention is increasingly recognized as a liability, particularly when managing hundreds or thousands of instances across mixed OS landscapes. Automation allows us to treat infrastructure as code, ensuring that tasks such as deploying server roles, configuring networking, and enforcing security policies are repeatable and consistent. By leveraging PowerShell on Windows and Bash on Linux, we eliminate the human error inherent in repetitive command line execution and create a standard baseline for our services. Beyond simple task execution, we will examine how configuration management tools like Ansible, Puppet, and Chef abstract these complexities into declarative states. This transition from manual configuration to automated workflows is not just about time saved, it is about verifiable consistency. When you automate, you move away from the fragile ClickOps mentality toward a verifiable, testable architecture. On the Windows side, PowerShell remains the primary engine for administrative control, utilizing commandlets that interact natively with Active Directory, local storage, and networking stacks. Effectively managing these environments requires understanding the pipeline architecture, which allows you to pass objects from one commandlet to another rather than relying on brittle text parsing. For example, gathering disk metrics and filtering them based on remaining capacity is a matter of piping results from a storage commandlet into a where-object filter. However, Linux environments require a different toolkit, typically centered around the text processing power of grep, awk, and sed. Bash scripts allow for sophisticated logic-based management, and when combined with cron for task scheduling, they provide a robust framework for log rotation, automated backups, and system audits. Understanding these two environments isn't just about syntax, it is about mastering the paradigms of object-oriented management versus text stream processing. When we scale our operations, we inevitably reach for cross-platform automation tools like Python to facilitate API interactions and complex orchestration. Python acts as a glue language, effectively bridging the gap between disparate services that do not share a common administrative language. For instance, you might use Python to query an IP address management system, verify the availability of a network endpoint, and trigger an Ansible playbook to deploy a required server role. This modular approach is essential not only for patch deployment but also for ongoing verification of those patches against an established threat model. By scripting the installation of server roles and features, we ensure that every instance is provisioned with identical security configurations, eliminating drift that often leads to vulnerabilities. Automation, when done correctly, inherently integrates security into the lifecycle of the server rather than treating it as an afterthought. Managing scripts effectively demands that we treat them with the same rigor as application code, which brings us to the necessity of version control with tools like Git. You should never execute a script in a production environment that has not been thoroughly vetted, version controlled, and tested in a staging or development environment. This workflow protects your infrastructure from cascading failures caused by a simple syntax error or an unintended logic branch in a script. Furthermore, a core component of production-ready automation is the secure handling of credentials. Hard-coding passwords or API keys in scripts is a significant security risk that compromises your entire infrastructure access model. Instead, we must utilize vaulting mechanisms or secret management providers to inject credentials at runtime, ensuring that sensitive data is never exposed in flat files or version history. Finally, consider the role of automation in health monitoring and log analysis, where the sheer volume of data makes manual human inspection impossible. Well-constructed scripts can parse system logs for common error patterns, aggregate findings, and generate alerts before a component reaches a critical failure state. By automating the analysis of log data, you shift from reactive troubleshooting to proactive capacity management. This is the ultimate goal of adopting automation practices, freeing the administrator from the drudgery of routine maintenance so they can focus on architectural improvements. It requires patience to script these processes initially, but the long-term reliability of your environment will justify the investment. Consistent application of these methods defines the mature, operational maturity that the Server Plus exam expects of a certified professional. See you in the next lecture. Welcome back. Today we are diving into the practical configuration of server roles and the underlying storage provisioning required to support them. When we talk about server roles, we move from theoretical architecture to the functional reality of providing services to end users. A web server, whether it is running IIS on Windows, or Apache or Nginx on Linux, acts as the interface for your applications. The configuration of these roles involves more than just installing the software package. It requires tuning memory allocation, handling worker process limits, and ensuring that the service is hardened against common web attack vectors. If you fail to configure the process isolation correctly on an IIS application pool, a single misbehaving site could potentially take down the entire web server instance. Similarly, in an Apache environment, balancing the NPM or multiprocessing module settings are essential to ensure the server can handle concurrent connections without exhausting system resources. Whether you are managing static content or complex dynamic applications, these role-specific settings form the foundation of your server's reliability. File and print servers often seem simple, yet they remain the backbone of most internal enterprise productivity. Configuring a file server requires a balancing act between accessibility and strict access controls. When you implement SMB for Windows environments or NFS for Unix-based systems, you are defining how data is presented to the network. Beyond mere access, you must manage storage growth by implementing quotas and file screens to prevent users from filling the space with unauthorized media or duplicates. The goal is to enforce governance over the storage infrastructure before a capacity issue triggers a production outage. Furthermore, enabling volume shadow copies allows users to recover their own deleted or modified files without needing IT intervention, shifting the burden of minor recovery away from your ticket queue. These mechanisms represent a mature approach to server administration where the system handles routine requests autonomously. As we move toward database and application servers, the complexity of tuning increases significantly. A database server is rarely a set-it-and-forget-it component. It requires meticulous configuration of memory, cache, and I/O scheduling. If your database engine is starved of memory, the system will swap to disk, leading to a precipitous decline in performance that no network upgrade can fix. Application servers introduce their own layers of complexity by acting as middleware that mediates between a client and the database backend. You must manage their threads, heap sizes, and session timeouts to ensure a consistent experience for the user. Monitoring these servers requires a clear understanding of the baseline, because if you don't know what normal behavior looks like for that specific application, identifying a bottleneck during peak hours becomes a matter of guesswork rather than methodical analysis. Storage provisioning is the physical and logical implementation of how that data actually lives on your disks. In a modern enterprise, you are likely working with a storage area network, or SAN, and the process begins by creating logical unit numbers, or LUNs. Once a LUN is created, you use iSCSI initiators and targets to bridge the gap between your server and the storage appliance. A key concept here is thin provisioning, which allows you to allocate more storage than you physically possess, relying on the assumption that not all users will fill their space simultaneously. While this is an efficient way to maximize your hardware investment, it introduces a significant risk if you do not monitor your actual storage growth. If you over-provision the underlying storage and the capacity is exhausted, the volumes will go offline, causing catastrophic failure. You must pair thin provisioning with robust alerting to maintain visibility into your actual allocation versus physical capacity. Finally, we address reliability through RAID arrays and high availability. Implementing RAID at the hardware controller level provides a layer of fault tolerance that protects against single or multiple drive failures, but it is not a backup. It is simply a way to keep the server running when media fails. When you combine this with high availability testing, you are confirming that your infrastructure can withstand a server failure without user disruption. You should regularly verify that your failover logic triggers at the right time and with the expected results. Troubleshooting these roles effectively involves tracking events, reviewing resource consumption logs, and ensuring that the server's underlying hardware is communicating correctly with the storage layer. When you master these configurations, you move from being a reactive administrator to a proactive engineer capable of sustaining complex environments over the long term. See you shortly. Hello everyone, and welcome back to our deep dive into the CompTIA Server Plus curriculum. In this session, we are stepping back to synthesize the breadth of knowledge required for the SK0-005 exam by reviewing the most critical pillars of server administration and infrastructure. We will consolidate our understanding of hardware, storage, networking, and the rigorous methodologies that define a competent systems administrator. This is not merely a rote repetition of facts, but an opportunity to see how these disparate components communicate and function within an enterprise environment. By connecting the architectural decisions of hardware with the operational realities of software and security, you will be much better prepared to handle the complex scenarios presented on the actual exam. Think of this as a final calibration of your mental model before we move toward the practical complexities of the remaining certification modules. We begin by revisiting the physical server layer, focusing on the distinction between form factors and the components that provide reliability, such as error correction code memory, known as ECC, and serial attached SCSI, or SAS, drives. When deploying storage, the trade-offs between RAID levels are paramount, where you must weigh the performance gains of RAID 0 or 10 against the data safety and parity overhead of RAID 5 or 6. Transitioning from physical to logical storage, you should keep the function of the host bus adapter, or HBA, clear in your mind, especially how it acts as the interface between the server and a storage area network using technologies like iSCSI or Fibre Channel to map a logical unit number, or LUN, to the operating system. These technologies underpin the entire storage strategy, and understanding exactly where the abstraction happens is critical for both configuration and troubleshooting. Virtualization and cloud delivery models further abstract these resources, requiring you to understand how hypervisors effectively carve physical host power into isolated virtual instances. Network protocols and administration tasks reveal the divergent nature of managing Windows versus Linux environments, where you must be fluent in both the PowerShell-driven automation of Windows and the shell-centric, file-based configuration typical of Linux partitions. This management layer relies heavily on tools like SSH for secure remote access, IPMI for out-of-band hardware management, and SNMP to report health metrics back to centralized monitoring consoles. These tools represent your eyes and ears in the data center, allowing you to react before a minor degradation evolves into a significant outage. However, technical management is incomplete without the strict, 6-step troubleshooting methodology that forces a methodical approach from identifying the problem to documenting the final resolution. Applying this process consistently ensures that you do not introduce secondary issues while probing for, or attempting to repair, the root cause of a failure. Security is not an add-on but a foundational element that must be integrated via Group Policy Objects, or GPOs, and enforced through robust multi-factor authentication, known as MFA, to verify identity across the infrastructure. When we consider the hardening of these systems, we must also view them through the lens of disaster recovery, where your recovery time objective and recovery point objective dictate the necessary frequency and type of your backups. Maintaining the physical environment is equally critical to this mission, as improper temperature control, humidity levels, or lack of physical access restrictions can negate even the most hardened software security posture. These environmental requirements, along with fire suppression and cable management standards, ensure that your data center remains a stable foundation for the business services it hosts. Everything we discuss here serves that primary objective of keeping the data secure, the services available, and the infrastructure performing within the defined parameters of a production environment. I will see you in the next lecture. Welcome back. We are now entering the phase of practical application where theoretical knowledge meets the realities of the data center. In this chapter, we will bridge the gap between abstract concepts and the hands-on performance-based questions that define the CompTIA Server Plus exam. You will learn to synthesize information from various technical domains to solve complex, multivariable problems that mirror real-world administrative tasks. My goal here is not to provide you with a static script, but to help you develop the architectural intuition required to remain calm when a server fails to boot or a storage array reports a critical error. We will navigate through storage provisioning, virtualization resource management, and incident response, ensuring you understand the underlying technical trade-offs. Successful server administration is rarely about memorizing isolated facts. It is about recognizing patterns and applying consistent methodologies under pressure. By the time we finish these scenarios, you will be equipped to evaluate business constraints like budget versus required redundancy when proposing infrastructure solutions. When we approach a performance-based question involving storage, we often start with the fundamental selection of a RAID level based on specific business requirements. If a request demands both high read performance and significant fault tolerance, we must evaluate the trade-offs between RAID 1, RAID 5, and RAID 10. RAID 1 provides excellent mirroring but carries a high cost of entry due to the 50% storage overhead. RAID 5 offers better capacity efficiency but incurs a write penalty because of the parity calculations performed for every transaction. RAID 10 provides the best of both worlds by combining striping and mirroring, though it requires an even number of drives and increased physical disk count. In a real scenario, you usually receive a constraint regarding the minimum number of available drive bays or a maximum budget for hardware. Your task is to match the technical capabilities of the controller and disk set to those constraints, ensuring you neither over-provision disks at the expense of budget nor under-provision them, risking data availability. Troubleshooting a server that fails to boot requires a structured movement through the components of the startup process, starting from the physical layer up to the operating system kernel. A common pitfall is to immediately suspect the operating system when the issue is actually a failed power-on self-test, POST, caused by a faulty memory module or a detached cable. We must utilize the 6-step troubleshooting methodology by first identifying the problem using console output or integrated Dell Remote Access Controller, iDRAC, logs. Once we establish a theory of probable cause, such as a corrupt bootloader or a misconfigured Unified Extensible Firmware Interface (UFI) setting, we test that theory systematically. If the boot error is related to localized storage, checking the status of the RAID controller cache or verifying drive health is a necessary prerequisite before re-imaging the OS. Moving cables or replacing components without verifying the state of the management controller often leads to cascading errors that hide the initial problem. Virtualization scenarios frequently present themselves as performance bottlenecks where a single workload is experiencing latency that impacts the entire host. We need to look at resource allocation, specifically checking for CPU contention or memory overcommitment that might be triggering swapping to disk. If a virtual machine is sluggish, the first indicator is often the hypervisor logs, which should be analyzed for signs of I/O wait times or network drop packets. You might find that the virtual network adapter configuration is incorrectly set, or that the virtual machine lacks the necessary integration services to manage the physical hardware effectively. When provision storage for these machines is nearing capacity, the thin provisioning settings can lead to unexpected outages if not monitored correctly. Efficient administration requires being proactive about these resource thresholds, as a reactive approach usually results in downtime that could have been avoided with better capacity planning. Network connectivity issues on a server often require isolating the problem between the physical interface and the logical IP configuration. If a server loses connectivity, we begin by verifying link lights on the NIC and checking the switch port status for flapping or duplex mismatches. Following the physical verification, we inspect the local routing table and verify that the default gateway is reachable from the server's network segment. If the server was recently moved, an incorrect VLAN assignment or a change in the spanning tree protocol (STP) state might be port blocking the traffic. Security policies must also be considered, as a misconfigured host-based firewall or an updated group policy object might be dropping ingress traffic that was previously allowed. By systematically eliminating these variables from the physical, data link, and network layers, we arrive at a clear diagnosis without wasting time on guessing common misconfigurations. Analyzing server logs to identify a security breach involves more than just reading the output. It requires filtering for patterns that deviate from standard operational behavior. Failed login attempts, unexpected privilege escalations, or access to sensitive audit logs during off hours are all indicators of a compromised environment. We must look across different sources, including system, security, and application logs, to build a coherent timeline of the incident. Often, the breach is detected when a service that usually performs minimal I/O suddenly begins flooding logs with errors or unexpected outbound connections. Incident response, in this context, is about isolating the affected host, preserving the evidence for forensic analysis, and verifying the integrity of the remaining systems. Understanding these indicators allows us to implement hardening measures that prevent future unauthorized access attempts while maintaining the availability of the production services. See you in the next session. Welcome to our review session covering the intricacies of server hardware installation and management. We will consolidate our understanding of physical components, lifecycle management, and critical out-of-band management interfaces to ensure you are exam-ready. When we approach the physical architecture of server clusters, we must first distinguish between blade and rack-mounted units, as their physical integration and power distribution profiles differ significantly. Rack-mounted servers offer high density but require meticulous cable management and airflow planning to prevent thermal hotspots, whereas blade servers utilize chassis-based power and networking, simplifying cable sprawl but increasing concentrated heat density. Central to these installations are the motherboard components, where CPU socket compatibility and strict RAM slotting protocols determine the baseline performance and memory throughput of the system. You should be familiar with the specific requirements for multi-channel memory architectures because improper population of these slots can lead to performance degradation or system instability. Beyond the silicon, the importance of physical peripheral connectivity, such as utilizing KVM switches for centralized console access or serial connections for dedicated management consoles, remains a foundational skill for headless data center operations. These connections serve as the bridge between the physical hardware layer and the remote administrator, ensuring that we maintain control even when the primary operating system or network stack is unresponsive. Turning our focus to the operational aspects, the management of power supplies and power distribution units is paramount in maintaining uptime in high-availability environments. Redundancy is not merely about having two power supplies plugged into the same source. It is about power path diversity that accounts for potential failures in the source circuit or the PDU itself. We must always consider the lifecycle stages of the hardware, starting from the planning phase where procurement aligns with capacity requirements, moving through deployment, proactive maintenance, and finally, the secure retirement and sanitization of assets. Asset management is fundamentally about documentation, as a server without accurate, up-to-date configuration records and physical labeling is effectively invisible during a troubleshooting event. When we examine BIOS and UEFI settings, the discussion must center on enabling essential features like virtualization extensions such as VTD and AMDV, which are prerequisites for modern hypervisor deployment. Similarly, the configuration of the Trusted Platform module is often required to establish a secure root of trust, which is a growing necessity for enterprise-grade hardware security compliance. Hardware-specific troubleshooting represents the intersection of electrical engineering principles and logical deductive reasoning. Thermal management issues often stem from failing cooling fans or obstructed airflow pathways, which underscores the need for regular physical inspections within the rack enclosure. Power-related issues, such as intermittent reboots or complete failure to post, frequently point toward deteriorating capacitors or the improper load balancing across redundant power modules. When you encounter a component failure, your approach must prioritize the implementation of hot swapping procedures, which allow for drive or power supply replacement without interrupting the flow of data or the availability of the service. This requires strict adherence to manufacturer-defined procedures for signaling the storage controller that a drive is slated for removal, thus preventing data corruption during the withdrawal phase. Furthermore, the role of out-of-band management interfaces like iDRAC, ILO, and IPMI provides an essential safety net, as these systems operate independently of the server's primary CPU and operating system. These interfaces enable remote power cycling, physical console redirection, and hardware health monitoring, which are instrumental when you are dealing with a server in a remote off-site facility. Successfully navigating the hardware domain requires a disciplined focus on both the physical standards and the management software that controls them. You should always treat the server environment as a holistic system where the failure of one small component, such as an incorrectly locked hard drive tray, can have ripple effects throughout the entire infrastructure. Remember that documentation is your primary asset during a disaster or a simple hardware upgrade, as it captures the intent and history of the physical setup. As you refine your knowledge in these areas, focus on the relationship between the physical limitations of the hardware form factor and the logical configuration settings within the BIOS or management controller. By maintaining a clean, documented, and properly redundant environment, you mitigate the majority of common hardware-related issues we encounter in the field. See you in the next lecture. Welcome back to our journey toward CompTIA Server Plus certification. Today we are focusing specifically on the high-level review of Domain 2, encompassing server administration and operating system management. Server administration is essentially the art of maintaining a stable, secure, and performant environment. When we discuss server operating systems, we are not just talking about the kernel, but the complete ecosystem that allows an application to run predictably across different hardware abstractions. Whether you are dealing with Windows Server or a Linux distribution, the underlying requirement remains the same. The system must handle resource scheduling, hardware interfacing, and security enforcement without introducing unnecessary latency. An administrator must understand how the specific architecture, such as a 64-bit microkernel, impacts the way applications utilize memory and CPU cycles. Choosing the right OS depends on the compatibility requirements of your stack, but the administrative burden often shifts based on the management tools available for that specific OS. This domain requires you to balance the need for granular manual control against the necessity of automated, repeatable configuration patterns that prevent human error. Directory services serve as the backbone of identity management within the enterprise, providing a centralized way to handle authorization and authentication. Active Directory remains the standard in Microsoft environments, utilizing LDAP under the hood to facilitate queries against objects like users, groups, and computer accounts. You should view directory services as a formal mechanism for enforcing the principle of least privilege. By associating permissions with roles rather than individual accounts, you simplify maintenance and reduce the likelihood of security holes created by permission creep. LDAP, or the Lightweight Directory Access Protocol, acts as the lingua franca for these services, allowing disparate systems to communicate with the directory to verify credentials or retrieve configuration data. Understanding how to structure forests, domains, and organizational units is vital for maintaining a clean, performant, and secure environment that scales with the needs of the business. Scripting and automation are no longer optional skills. Every modern administrator must possess the ability to codify repetitive tasks. When you move beyond performing one-off updates, you begin to see the infrastructure as code, where manual configuration is replaced by scripts that ensure consistency. Patch management, driver updates, and basic monitoring tasks should be handled by automation cycles that track version control. This approach minimizes the risk of configuration drift, where individual servers unknowingly evolve into states that deviate from your established security baseline. When you execute a script, you are essentially documenting the state of your infrastructure in an executable format. If a server requires a specific security patch, that action should be deployed through an automated pipeline that tests the change in a staging environment before pushing it to production. Monitoring server resources provides the empirical data required for performance tuning and capacity planning. By tracking baseline metrics for CPU utilization, disk I/O, memory pressure, and network throughput, you can identify bottlenecks before they manifest as service outages. When an application experiences performance degradation, the first step is always to examine the resource consumption patterns over time rather than making reactive changes. Optimization often involves adjusting the resource allocation for virtual machines or refining the disk indexing and file system permissions to improve access speeds. As your infrastructure grows, this monitoring phase must transition into a proactive activity that informs your hardware refreshes and cloud deployment strategies. Never assume that a system configuration remains optimal indefinitely, because workloads change and usage patterns inevitably shift over time. The shift toward virtualization and cloud deployment has fundamentally changed the concept of the server lifecycle. In an infrastructure-as-a-service model, your responsibility focuses on the operating system and the applications, while the provider handles the underlying physical hardware and virtualization layer. This shared responsibility model clarifies where your security obligations begin and where they transition to the provider. Furthermore, proper server decommissioning is a critical yet often overlooked aspect of lifecycle management. Data destruction must follow industry-standard procedures, such as NIST guidelines, to ensure that sensitive information remains unrecoverable after a disk or server is retired. Whether migrating to the cloud or cleaning up on-premises resources, the goal remains the same: ensuring that every asset is accounted for, managed effectively, and disposed of according to security policy. See you in the next lecture. Welcome back to our final review sessions where we consolidate the vital concepts required to excel on your certification exam. Today we will systematically revisit the critical components of Domain 3, focusing on the interplay between robust security postures and resilient disaster recovery strategies. We start by examining data protection, where we distinguish between data at rest and data in transit. Encryption at rest typically involves full disk encryption or file-level encryption using standards like IS to ensure that physical theft of a drive does not equate to data loss. Conversely, protecting data in transit requires secure protocols like TLS, which wraps communication in a cryptographic tunnel to prevent interception during transmission. You must understand that these are not merely checkboxes for compliance, but foundational necessities for maintaining the integrity and confidentiality of your server infrastructure. When we discuss hardware and software hardening, we are essentially talking about reducing the attack surface by disabling unnecessary services, closing unused ports, and applying the principle of least privilege. A hardened server is a predictable server, and unpredictability is the enemy of security in any enterprise environment. Physical security and environmental monitoring are often overlooked in software-centric discussions, yet they remain the bedrock of availability. Controls like biometric scanners, badge readers, and video surveillance are your first line of defense against unauthorized physical access to the rack or data center floor. Complementing these are environmental sensors that track temperature, humidity, and airflow, because a perfectly secured server is useless if it melts due to a failed cooling unit. Moving into high availability, we utilize clustering and load balancing to ensure that if one node fails, the service remains accessible. Load balancing distributes incoming traffic across multiple servers, while clustering allows multiple nodes to operate as a single logical entity, sharing resources or providing failover capabilities. These are architectural decisions that must be baked into the design early on, rather than bolted on as an afterthought once an outage has already occurred. Disaster recovery planning introduces the specific metrics that define your organizational tolerance for downtime and data loss. The recovery time objective, or RTO, represents the maximum allowable duration of downtime, while the recovery point objective, or RPO, indicates the maximum amount of data, measured in time, that your organization can afford to lose. To achieve these objectives, you rely on a solid backup strategy, and the industry standard remains the 3-2-1 rule. Keep 3 copies of your data on 2 different media types, with at least 1 copy stored offsite. Your recovery sites, categorized as hot, warm, or cold, provide the infrastructure necessary to restore operations, each representing a trade-off between cost and speed of recovery. When a security incident occurs, your response must be guided by a formal plan that includes identification, containment, eradication, and recovery. Adhering to these structured steps prevents reactionary mistakes that often exacerbate the initial scope of a breach. Authentication and authorization are the final pieces of this security puzzle, ensuring that identities are verified and permissions are scoped correctly. Multi-factor authentication adds that necessary layer of friction beyond simple passwords, while role-based access control ensures that administrators only possess the permissions required for their specific tasks. Protocols such as Kerberos are widely used in enterprise environments to provide strong authentication across distributed systems, relying on a trusted third party to issue tickets for service requests. Beyond simple access, we utilize tools like firewalls, intrusion detection systems, and intrusion prevention systems to monitor and police the traffic flowing across our segments. Endpoint protection completes the picture by providing localized security on the server itself, scanning for suspicious patterns or known malware signatures. Regular security audits and compliance checks are the only way to verify that these controls remain effective over time, as configurations tend to decay due to human error and evolving threats. I look forward to continuing this synthesis of topics in our next review session. Welcome back. Let's refine our understanding of troubleshooting methodologies and the diagnostic tools essential for passing the Server Plus exam. In this session, we will consolidate the core troubleshooting patterns and specific utilities that bridge the gap between theory and practical server maintenance. Effective troubleshooting is rarely about guesswork. It is a disciplined, step-by-step process that systematically narrows the scope of a problem. CompTIA demands that you adhere to the 6-step methodology, starting with identifying the problem through information gathering and user reporting. Once the issue is defined, we establish a theory of probable cause, prioritizing those that are simplest to verify first. Testing that theory follows immediately, and if our hypothesis proves incorrect, we reassess and consider alternative causes. After identifying the root cause, we implement a solution, which often involves testing in a controlled environment to ensure no collateral damage is done. Finally, we verify full system functionality and document the findings, which is a step often skipped by junior technicians but vital for organizational learning. Hardware and environmental issues often manifest as non-booting servers or intermittent performance degradation. Power-on self-test failures, or post errors, typically indicate faulty essential components like RAM or CPU, while overheating is often a byproduct of blocked airflow or failed intake fans. Disk failure is another frequent hardware hurdle where we shift focus to RAID status indicators and physical drive status lights. When addressing these items, we rely on hardware-specific diagnostic utilities provided by vendors, which are far more precise than general OS-level reports. Environmental monitoring, including humidity and temperature sensor logs, should always be the first place to look when multiple servers experience hardware faults simultaneously. By focusing on the health of the base layer, we prevent time-consuming software debugging attempts that would ultimately prove fruitless. Software and service troubleshooting focuses on the layer where the kernel interacts with drivers and applications. OS crashes, often represented by blue screens or kernel panics, almost always lead us to review system logs, such as Event Viewer in Windows or syslog in Linux. Service failures usually stem from incorrect configuration files, expired certificates, or dependencies failing to initialize at startup. When a boot issue occurs, we investigate the bootloader environment and check for corruption in system partitions or missing boot files. Command line tools like SFC or DISM serve as first response repair mechanisms for OS integrity, provided we have gathered sufficient environmental data prior to intervention. Maintaining a clean baseline through images or documented configuration states allows us to perform diff-based comparisons to see exactly what changed before the service became unresponsive. Networking and storage troubleshooting require a strong grasp of connectivity and data path flow. For network issues, we utilize ping to verify reachability, netstat to inspect active port listeners, and map to identify open services across the segments. If we suspect path latency or packet loss, trace-based utilities provide the visual evidence needed to determine if the fault lies on our local fabric or beyond in the routed environment. Storage issues, particularly with SAN connectivity, involve verifying multipath I/O configurations and checking fabric zoning. RAID rebuilds are a high-stress maintenance task where the primary goal is ensuring the controller can perform the parity recalculations without being overwhelmed. We must constantly monitor I/O wait times during these recovery procedures, as they represent the single biggest bottleneck to operational continuity. Performance bottlenecks are rarely hidden. They are typically visible through resource metrics if you know where to look. CPU saturation often points to poorly optimized processes or runaway threads, while high memory utilization might indicate a memory leak in a poorly managed service. I/O bound systems usually signal a mismatch between the storage provider and the application demands, often fixed by adjusting block sizes or adding cache. When we analyze these statistics, we must correlate them with documented baseline performance to distinguish between normal peak hours and genuine degradation. Once we identify the bottleneck, we follow our established change management procedures to apply remediation, ensuring we document the impact of the changes for future reference. Without documentation, you are merely patching symptoms rather than solving systemic problems. Escalation is a critical part of a professional workflow, and understanding when to involve a vendor or a senior contributor is a sign of maturity, not incompetence. We escalate when our localized troubleshooting reaches the boundaries of our administrative scope or when the time to repair exceeds the agreed-upon service level agreement. When escalating, the quality of our documentation becomes the most important asset we provide to the next team. We include steps already attempted, logs gathered, and the observed outcome of every failed theory. This prevents the senior team from repeating dead-end diagnostic steps, which significantly reduces the mean time to repair. Effective troubleshooting lives and dies by our ability to communicate the current state of a complex system to someone else. See you in our next session. Welcome back. Today we refine your preparation by analyzing the structure and expectations of the final comprehensive practice exam. To succeed in the SK0-005 exam, one must move beyond rote memorization and understand how CompTIA structures its assessment engine. The exam spans 90 minutes and requires a scaled score of 750 out of 900, which leaves very little margin for error across the 4 major domains. You will encounter both traditional multiple-choice questions and performance-based items that simulate real-world server administration tasks. When approaching these questions, treat them as a diagnostic challenge where you must isolate the core intent of the question. The test developers often include distractors that look technically plausible but do not address the specific scenario presented. If you find yourself struggling with a question, look for keywords like first, most, or least, as these are binary indicators that prioritize one action over another based on standard ITIL or CompTIA troubleshooting methodology. Managing your time during those 90 minutes is essential for maintaining accuracy under pressure. Many candidates lose valuable points by spending too much time on a single complex performance-based task early in the exam. It is often better to flag complex items, move forward to answer the faster multiple-choice questions, and return to the complicated tasks once you have secured the easier points. This prevents the scenario where you run out of time while stuck on a single configuration issue. Regardless of whether you are testing at a physical center or via an online proctored environment, ensure your workspace is compliant and that you have accounted for the necessary pre-check procedures. Fatigue is a genuine risk, so try to balance your pacing to remain analytical throughout the entire duration of the session. As we reach the final stage of your preparation, you should perform a mental audit of mission-critical values that frequently appear in testing scenarios. You must be able to recall common service port numbers and their associated protocols without hesitation, as these are foundational to network troubleshooting. Similarly, the nuances of RAID levels are frequently tested, specifically regarding the disk redundancy, write performance, and minimum drive requirements for systems like RAID 1, 5, 6, and 10. When you review your practice performance, do not just count your correct answers. Spend equal time investigating why you selected an incorrect option. Identify if the error was a gap in technical knowledge or simply a failure to read the prompt completely. By systematically eliminating distractors through this process of elimination, you increase your statistical probability of selecting the intended best practice answer. See you in our next discussion. Welcome to this final preparation module, where we will refine your approach to the testing environment and solidify your exam day strategy. We are going to cover everything from logistics to cognitive management to ensure you perform at your peak when it matters most. Preparation for the actual exam day begins with logistics, specifically choosing between an in-person testing center or the online proctored environment. If you opt for the online exam, you must perform a thorough system check on the exact computer and network connection you intend to use on test day. This involves verifying that your internet speed is stable, your microphone and camera function correctly, and that no prohibited applications are running in the background. If you choose a physical Pearson VUE testing center, ensure you have your route planned and arrive at least 15 minutes early to complete the security check-in procedures. You are required to provide 2 forms of government-issued identification, one of which must have a photograph and a signature, so do not leave these sitting on your kitchen table. Failing to meet these strict identity verification requirements will result in being turned away without a refund, which is an unnecessary administrative hurdle to face before even starting the assessment. Regarding the test itself, you should expect a maximum of 90 questions, which may include both multiple choice and performance-based questions, often referred to as PBQs. These PBQs are simulated environments or complex scenarios that require you to apply your knowledge rather than simply recall definitions. When you encounter a particularly difficult question, do not linger on it and allow your stress levels to rise, as this is a common trap that depletes both time and mental energy. Instead, utilize the flagging feature to mark the item and immediately move on to the next question. This strategy allows you to maintain your momentum and ensures you do not waste precious minutes on a single problematic query while potentially missing easier questions later in the exam. You can return to your flagged items once you have completed the rest of the set, provided the clock has not expired. Mental management is just as important as technical knowledge during these 90 minutes of intense focus. It is perfectly natural to feel a spike in anxiety when faced with a challenging prompt, but recognizing that this is merely a physical response allows you to regain control. Take a moment to regulate your breathing if you feel overwhelmed, as clear thinking is your most significant asset during this assessment. Remember that the exam is designed to be difficult, and you are not expected to know every minute detail perfectly. If you find yourself stuck, reread the prompt to ensure you have identified the specific goal of the scenario, whether it involves security, performance optimization, or disaster recovery. Confidence comes from knowing how to navigate the test structure, not from knowing the answer to every single edge case in the vast CompTIA syllabus. In the final hours leading up to the exam, avoid cramming new material and instead focus on reinforcing the most commonly confused concepts. For instance, clearly distinguish between incremental and differential backups in your mind. Incremental backups only capture data that has changed since the last backup of any type, while differential backups capture all data changed since the last full backup. Misunderstanding these foundational definitions can lead to errors in disaster recovery scenarios that might appear on the exam. Review your understanding of redundancy and RAID levels, ensuring you grasp the trade-offs between speed, cost, and fault tolerance for each configuration. If you can explain these concepts to an imaginary colleague, you possess the requisite depth. But if you find yourself hesitant, quickly review your notes one last time. Once you have successfully passed the exam, remember that your certification maintenance requires a commitment to ongoing professional development. CompTIA uses a Continuing Education Unit, or CEU, system to ensure that your skills remain relevant as technology evolves over the 3-year renewal cycle. You can earn these credits through various methods, such as attending training sessions, completing higher-level certifications, or participating in industry events. Staying proactive about this process avoids the need to retake the exam later and keeps you engaged with the community. Transition fully from your study mindset into a professional execution mode, knowing that you have thoroughly prepared for the challenges ahead. Good luck with your final preparations, and I will see you in the next lecture. Welcome back. In this final discussion, we will synthesize the comprehensive knowledge you have acquired across our server administration curriculum and outline the practical steps toward your professional certification. We began this journey by establishing a fundamental understanding of server hardware, where we explored various form factors, thermal considerations, and the nuances of component installation. From there, we moved into the software layer, analyzing how operating systems manage resources and how identity and access management frameworks ensure that only authorized entities interact with sensitive data. Our deep dive into storage technologies allowed us to grasp the complexities of RAID configurations and the performance trade-offs associated with different storage architectures. We then shifted our focus to virtualization and cloud integration, which are no longer optional skills but core competencies in modern data center management. By examining networking services and server security hardening, we bridged the gap between physical machinery and the abstract, interconnected environments that define contemporary infrastructure. Finally, we refined your approach to troubleshooting, shifting from reactive guesswork to a structured, methodology-driven process that minimizes downtime and facilitates rapid incident resolution. Reflecting on these core competencies, you should now possess a holistic view of the server lifecycle, spanning from initial deployment and configuration to long-term maintenance and disaster recovery. Understanding physical server hardware is only half the battle. The other half lies in your ability to document changes, implement power redundancy strategies, and automate repetitive tasks through scripting. These skills form a coherent toolkit that allows you to maintain high availability in production environments. As we explored the documentation and best practices domain, you likely noticed that technical expertise is ineffective without a corresponding set of standard operating procedures. By masterfully combining technical capability with process-oriented management, you position yourself as a reliable engineer capable of assuming responsibility for critical business infrastructure. This balance of hard technical knowledge and structured methodology is exactly what the industry demands from certified professionals. The CompTIA Server Plus certification marks a definitive milestone in your career, and reaching this point requires both persistence and significant mental effort. If you have mastered the material presented, you are well prepared to register for the official exam through the Pearson VUE platform. Once you pass, CompTIA will issue your digital credentials, which you can verify and display via the official certification portal. While Server Plus is currently designated as a professional credential that does not require formal renewal, staying current with industry shifts is imperative. Technologies such as high-density storage, container orchestration, and software-defined networking are continually evolving, and your professional value depends on your curiosity and commitment to self-directed learning. Use this certification as a stable foundation upon which to build deeper, more specialized expertise. Looking toward your future roadmap, you might consider how your newly acquired knowledge intersects with cloud-centric pathways. If your interest leans toward infrastructure scalability and services, CompTIA Cloud Plus offers a natural bridge that explores virtualized compute and storage at scale. Conversely, if you find that securing these environments is your primary focus, The Security Plus path provides the rigorous focus on threat mitigation and risk management you will need to defend complex architectures. For those pursuing vendor-specific roles, moving into AWS or Azure associate certifications will allow you to apply the principles of server administration to specialized, provider-managed platforms. Alternatively, pursuing certifications through the Linux Professional Institute will deepen your expertise in the open-source systems that underpin the majority of global internet infrastructure. Choose your next path based on the specific operational domains where you wish to exert the most influence. I appreciate the effort you have put into this comprehensive review of server administration and data center operations. Pursuing a career in this field implies a commitment to stability, reliability, and precision, and I hope this course has provided the clarity necessary to navigate these environments with confidence. Every challenge you encountered throughout these lessons mirrors the reality of a production server room, and your ability to work through those concepts signals your readiness for professional practice. Keep refining your skills and maintain the mindset of a lifelong learner as you progress through your IT career. Good luck with your upcoming exam and your future professional endeavors. See you in the next stage of your career.